world where space and time are intertwined, one man dared to challenge the status quo. His name, Dayton Miller.
All right, hello and welcome everyone to Celestial Theodolite update number 40. Tonight, before we get into it, quick announcement. My internet is lagging too hard whenever I try to stream, so I'm just going to record this episode. Obviously, we're live on Gio's channel, so we'll get the same live experience or whatever. But anyway, we got a couple of things to talk about, so Mike's going to open this up with a little Prezi that he made, and then we're going to go over the data analysis of what Astronomy Live put forward in the debate regarding the airplanes. So we'll get into that, and then we'll take some questions, and then wrap up for the week. And I know I said this week we were going to do where we were going to get to Ruhif's contentions to the 15 questions, and then John's Prezi, and I think that other gentleman who did the distances or whatever. But not doing that yet. The plane data takes precedent because that's a hot topic right now. So we're going to get into that afterwards. So, Mike, whenever you're ready, sir, go ahead and start.
Okay, I'll get started, and I already mentioned that I'm in the Sonoran Desert in Arizona, just north of Tucson, in a string camper. So I could lose, and a storm is passing by. I could lose my connection, and if that happens, Alan's going to take over for me. I want to talk a little bit about what we've all been experiencing for the last year. I'm going to start with a definition of misinformation. Misinformation is false, inaccurate, or misleading information shared without the intention to deceive or cause harm. We don't always know what people's intention is, but we should all train ourselves to call it misinformation, even when we believe it's a deliberate lie. And please think of it as zeal rather than malice. During the past year of self-deal updates, has been, it seems like, an excessive amount of misinformation coming from some participants in the forum. And we can, of course, all be a little overzealous at times. And in our zeal, we may not realize we are sharing misinformation. So we should all be careful to avoid sharing misinformation. Not everyone shares my philosophy, but I believe that misinformation deserves a close examination and a thorough discussion. So we should all try to be kind to the person who misinforms us. That's why Alan has been so careful examining the refraction claims of our globe Earth friends. And
Hey,
although
Dr. Mike,
misinformation,
if are your slides supposed to be updating with this as well?
no, it should be stuck on a misinformation slide.
Okay, perfect. Gotcha. Just wanted to make sure. Okay, sorry for interrupting.
Yep, I may wait when I change slides just to make sure I get feedback that it changed okay because of my connection. So I'll do that, and I'll ask you, did it change? Um, although misinformation can be frustrating, both Alan and I share the philosophy that it serves the beneficial purpose of motivating us to more carefully examine the data. And I'm telling you that because certain antagonists misread the significance of peer reviews that are critical, where we're critical of each other. That is not conflict or us disagreeing with each other. It is just good science. And I'm going to change slides now. Did my slide change?
Yes, sir.
Speculation? Was that a yes?
Yes, sir.
Okay, thanks. So here a definition of speculation is the act of making a guess or prediction about something, often without having all necessary information. There's a big difference between asking, could it be that, and erroneously stating that so-and-so believes something. In the past year of self-theo updates, there's been an excessive amount of speculation coming from some participants in this forum where they'll tell you somebody said something that they're speculating they said. They didn't actually say that, or it was misinformation. So we should all challenge speculation. as soon as we realize participants are guessing about things without sufficient information or based on misinformation. I'm going to change slides again. And this one should say speculation about misinformation. So as bad as misinformation and speculation are separately, speculating about misinformation is the worst thing we can do. It's the worst of all. During a debate, it's easy to attribute malice to your opponent, and whether that's true or not, we should all be as respectful as we can to each other. Sometimes we are fighting our own zeal or strong emotions, but it's important to treat each other with respect. And I'm moving on to a slide about logical fallacies now. Logical fallacies are a flaw in reasoning that renders an argument invalid, unsound, or weak. During the past year of Celestio updates, there have been many logical fallacies coming from some participants in this forum. Logical fallacies are errors in logic. They often use deceptive tactics, irrelevant points, or mistaken beliefs to mislead, distract, or persuade, even if the argument seems temporarily convincing because that's what they're doing. Logical fallacies can be hard to spot, so we should all remain alert and challenge everything that doesn't seem accurate or seems like a logical fallacy. But please make a note and challenge later rather than interrupting whoever is speaking. So I think we should be kind above all. So on to the next slide about being kinder and gentler. And I'm sorry for sounding a little preachy. I'm calling on members of this forum to attempt kinder and gentler debates and discussions. Please stifle your zeal and exhibit gentle human kindness. And I'm now going to address some specific speculation and or misinformation concerning me and the concept of celestial theodolite. And I've been trying not to jump in and give everybody their chance to say things, but that's led to a lot of misinformation and speculation. And if you hear my dog barking, I'm sorry. He's triggered by something he sees.
It sounds like he's cheering you
So
on. He's like, "Go, Dad, go! You're crushing
could
it."
be. He could be saying, "Go, Dad," for all I know. Sadly, I don't speak Great Pyrenees. So speculation about and misinformation about me. Some people foolishly speculate that I never believed in a globe Earth. I call that foolish, even though that may not be kind, because most of us were indoctrinated since childhood belief in, to believe in a globe Earth. So it's just foolish to speculate I never believed in a globe Earth. On top of that, my entire 50-year career was spent working with satellites on various special access programs for the government. Um, so I'm heavily indoctrinated. Um, most of my career was devoted to developing various systems that ultimately automated what eventually became the U.S. Space Force. And at the age of 70, I retired on the day the U.S. Space Force began. And as you can imagine, I was very heavily indoctrinated to believe in a globe Earth in that environment. During that time, a non-disclosure agreement prevented me from writing any unapproved books during my entire career. I retired, that non-disclosure agreement was revised to prohibit me only from writing about my work on special access programs. So consequently, with my non-disclosure agreement restrictions lifted, I immediately wrote 3 books in 2020. The theme of all 3 of those books is the search for truth. And anyone who has Kindle Unlimited can borrow my books free of charge. If you borrow those books, please skim through all of the pages and read any pages that look interesting. My first book about Prime number 17 documents many things I began questioning at the start of my search for truth. It's a book of few statements but many questions. My second book about the scientific method questions science. It makes the bold statement that science has always been wrong, science is wrong now, and science will always be wrong. That book advocates a return to the scientific method of 2 centuries ago, which was based on experiments rather than models. And as my third book evolved, I realized it needed to eliminate the rambling. Instead of publishing it, I spent the next 3 years revising it. Now, some of my antagonists are zealous to point out that my many books are essentially self published. I made that choice because I didn't want a publisher to buy the rights and then suppress or spin the information I was trying to present. So my third book deals with my discovery that the luminiferous ether it does exist and that it explains all of the fundamental constants of physics. It's explained in the book, and my GitHub repository contains additional software that supports my claims to a Six Sigma level of confidence. And in addition, I also have a YouTube channel with a few short videos about various topics from the book. It has been widely claimed that the Michelson-Morley experiment debunks the concept of luminous ether. That is a gross misinterpretation of their experiment. What the Michelson-Morley experiment actually did was to debunk the concept that of Earth moving through the ether during its alleged orbit around the sun. You can find that and many other good discussions about that topic in the Ether Cosmology archives. My book about the luminiferous ether led to an invitation to present my findings to the Ether Cosmology Discord channel. I had no idea at the time that many members of that group believe the Earth is flat. And watching some of their presentations and debates, I was amazed at the obnoxious behavior from the opposing side of the debates. It was my side of those debates. So I asked if I could give a second presentation to the Ether Cosmology group about how to use the null hypothesis during debates. After giving that presentation, I sensed it was a difficult concept for many, so I developed a different example of a null hypothesis that was more appealing to them. And that, at that time, I personally still believed my indoctrination that the Earth was a globe. I asked myself, how would I use the null hypothesis to prove that? Those of you who are familiar with the null hypothesis, please note that I'm using the original terminology rather than the more modern reversed terminology. I prefer to always go back to the original meanings of things, and the word null in null hypothesis refers to the not subscript of the hypothesis that needs to be found false. It's common for a simple hypothesis to contain many assumptions and variables that can never be proven. So instead, it's essential to refute the opposite and mutually exclusive null hypothesis. And you should remember to always keep it short and simple. And for those who aren't familiar with the null hypothesis and want to learn more, you can find that on my Discord channel. Sorry, not on my Discord channel, on my YouTube. On my GitHub channel. Sorry, I'm fumbling around with this. I don't know where I stuck things. I recently sold my ranch in Colorado and returned to Arizona, where most of my family lives. Pikes Peak was easily visible from my ranch, so it became my initial choice to attempt to refute null hypothesis while I still lived in Colorado. From the flat Earth perspective, the flat Earth angle to Pikes Peak should be about 2 degrees 31 arc minutes, and the globe Earth angle to Pikes Peak should be about 2 degrees 17 arc minutes. And that is under ideal conditions without correction for refraction. The most important thing to understand is that if the Earth is a globe, the angle to Pike's Peak cannot be near the 2° 31 arc-minute flat Earth angle. It must be closer to the 2° 17° globe Earth angle. On a flat Earth, the angles at the peak and for the observer are identical congruent angles. On a globe Earth, that cannot be true. So it should have been easy to demonstrate that the null hypothesis was false. For my initial experiments, I used terrestrial measurements. A modern terrestrial theodolite measures 2° 17 arc-minute globe Earth angle, but an antique theodolite measures the 2° 31 arc-minute flat Earth angle. In other words, there was a discrepancy between what those terrestrial devices measures. That discrepancy quickly led me to realize there's a great deal of misinformation and speculation surrounding the globe Earth theory. Among other things, I almost immediately discovered that refraction has been a continuous problem with all terrestrial theodolite measurements of mountain peaks. By the time I devised an experiment, I also realized that terrestrial theodolites were being used far beyond their range of accuracy, and that the results were inconsistent based on the age of the device. And then further, my studies of refraction made it immediately obvious that the hypothesized curvature of Earth was built into celestial refraction equations. That's why our globe Earth friends are so emphatic that terrestrial refraction is not the same as celestial refraction. In fact, they often want to use both to make their measurements seem more accurate. So to completely bypass the problem of refraction, just over a year ago, I proposed using mountain peaks as the horizontal crosshair of a celestial theodolite, and then using the true elevation of the star. Excuse me, I'm going to take a sip of water. I propose using the true elevation of the star at the time of occlusion to compute the altitude of the peak. The true elevation of the star doesn't need correction because it reports where the star actually was rather than where it appears to be. The celestial theodolite concept consists of recording what time a peak occludes a star and then using the elevation of the star to compute what the altitude of that peak was. So, excuse me, not the altitude, but the height of that peak. In other words, the rise above the observer. It is that simple. In that way, it doesn't matter where the peak or the star appear to be, nor what path the starlight took before it disappeared. The only thing that matters is that it was the peak that occluded the starlight, not a mirage of the peak, but the actual peak. That has become a hotly debated topic because without refraction corrections, the globe Earth hypothesis completely fails due to Euclid's theorems. And Alan has talked about it a lot. I want you to remember the null hypothesis. If refraction is really a factor, refuting the null hypothesis should work. But it doesn't work. Many claim it works for globe Earth. Slide after next will show that it demonstrably does not work better. And to understand the next slide, you first need to understand the math it uses is just simple plane trigonometry. It isn't some unique Heffron angle, as some antagonists falsely represent it. Height above the observer's eye is simply the distance to the peak times tangent of the true elevation of the occluded star. And the deviation is that calculated height minus the actual rise of the peak above the observer's eye. All of that's easy to calculate, and but all real-world measurements contain small deviations. This may be due imprecise altitude, distance, even terrain, or many other factors. We have a lot of debates about those minor deviations, but the deviations are usually not very significant. So the debates are often more of a red herring to get us off the topic we're really discussing. This is the graph I was talking about that was coming up. And this graph demonstrates the deviation of flat Earth from its predictions in fuchsia, which is a color that's similar to magenta, and the deviation of globe Earth predictions from the globe Earth from its predictions, and that's in green. It's very obvious from this graph that flat Earth predictions are much closer, and that's why our globe Earth friends add refraction to make their predictions appear to be more accurate. This graph does not include refraction. It's just the raw globe Earth prediction without corrections for refraction. That is why our globe Earth friends put so much emphasis on appearances. Appearances based on refraction is the very thing the celestial theodolite was designed to eliminate, so that by accurately measuring the true elevation of stars at the time the mountain peaks occlude their light, we can know what the real angle was. And to be clear, fuchsia error is how much elevation of the stars on the peak deviate from flat Earth predictions, and the green error is how much the elevation of stars at the observer's location deviate from globe Earth predictions when they're not allowed to manipulate those predictions using so-called refraction. An inconvenient truth for our globe Earth friends is that when you subtract their alleged globe drop, and they also call that d squared over 2r, from the flat Earth error, that exactly equals the globe Earth error. In other words, the globe Earth error is entirely due to the complete absence of the globe drop that our globe Earth friends predicted. I want you to think about that. Without refraction, globe Earth measurements deviate from flat Earth measurements by the exact amount our globe Earth friends claim is curvature of the Earth, which they sometimes call globe drop. To hide that inconvenient truth, our globe Earth friends add exactly the amount of refraction needed to make their predictions appear to be accurate, even though they're not accurate. The green deviation for globe Earth in this diagram uses the uncorrected elevation of the star at the observer's location. Much has been made of those big deviations between Greenhorn Mountain and North Peak. They are actually further evidence for a flat Earth, and I'll be explaining that. Greenhorn Mountain and North Peak were so far away from my old house that Stellarium claim those stars were far below the horizon. The big number for globe Earth results from that erroneous belief that the stars are under the curvature of the globe Earth at the time of occlusion. Big number for the flat Earth deviation from prediction at the distance of those peaks was my fault. At the time I proposed the celestial theodolite, I still believed that a globe, I still believed in the globe. And so when I devised the self-theo technique, I failed to compensate for the fact Stellarium calculates that stars rotate beneath a globe. I didn't yet understand the impact of stars appearing to hover as they rotate toward the horizon of the flat Earth rather than going under the globe as our globe Earth friends claim. In fact, I didn't have a very good understanding of that until some analysis I did recently. So I want you to please take a moment to look at this graph and then begin asking any questions you may have, or if Alan wants to go someplace else first, that's fine.
No, we're good. Does anyone have any questions or comments? So one of the, if no one has anything, I'll go ahead and help build off of that. One of the things that I had noticed, and I'll pull up some graphs here to help supplement. Give me 1 second.
Should I go ahead and stop my screen share?
Yeah, sure. Yeah, here we go. All right, let me get my screen share open. Open link. Okay, so this graph here, plotting out these celestial spheres. So following that 60 nautical mile per degree, using the celestial sphere model that's tied to the fictitious observer at the center, which is how they merge it with the terrestrial sphere. But yeah, so this blue line is what they would predict for the true positions, and then this is the deviations at the time of occlusion from that. So that hovering you were calling it, we've been calling it a lingering, and yeah, stellarium doesn't account for any of that sort of aspect of it because it's based off of linearizing that 15 degrees per mile at sidereal time, because that's what defines the geographic position. So like they're always trying to reference that, so they need that hard constant or whatever. So there's no accounting for anything like that happens. So that's been my thoughts on the measurement deviations, because what we see here, before we get to this, another thing you touched on was how the globe drop over distance added to the flat earth air in the measurement equals the amount that the globe was off by their measurement, which is accounting for drop over distance, showing that it cancels out, meaning that it's like a systemic error that's not present due to like uh any geometry factors or whatever. It's just showing up in the math because it's in the math, but it's not a real consequence of reality. So let me see if I can pull those up real quick to show some supplemental graphs to that. Peak analysis, is that? No. No. Hang on. I added all this new stuff, but I can't remember where I added it. Is it errors? Analysis. Okay, 1 second. Here we go. It's under central angle analysis. Okay. Central angle analysis. Here we go. Sorry about that. All right, gentlemen. So we see here we have the orange is whatever the drop over distance will be. The green is the flat Earth air, and then the globe Earth air is on the side here. So what we're looking at for Pikes Peak, for example, this 2 arc minute difference from our prediction versus where the star was. We take that intersection difference. That's going to be our intersection flat Earth right here. So that's what that is supposed to represent. And then the globe Earth prediction for the observer centric position, we have the true position for the observer minus where it was supposed to intersect at from the raw geometric globe angle, and then that is 11 arc minutes. Now, what we noticed a long time ago was that if you add these two errors together, it equals the drop over distance of the arc length, or the half gamma as we've been calling it. So that's the relationship there. And then to show what happens when we add them, they cancel out. So in this case, the arc length was 2 arc minutes from being fully traversed. So there's a negative value there. So in order to prevent the graph from moving it down below the zero and making it look all uneven and what have you, it puts it on top, but it scratches it out. So just the orange bar is level with the pink bar. That's what we're looking at here for Pikes Peak. And then we'll see that again on another peak when where that negative happens. But here's a nice clean view of it. So for Blodgett Peak, the flat Earth intersection difference was 5 arc minutes. You add that to the drop over distance, it equals what the globe, how much they missed theirs by. So that's what Mike was talking about when he was showing that graph with the d squared. What was the equation? Can't remember now, but whatever it was for the drop over distance, uh, in comparison, that's what he was talking about. When you add that to our air, it exactly cancels out what the globe missed theirs by, showing that geometric relationship. And of course, that's a relationship that is bound by central angle theorem. So for those of you who aren't familiar with central angle theorem, this is how all of that is intertwined and how there's a drop over distance mathematical value that's not being present in the measurements, and like in reality it's not, the measurements aren't leaning towards the intersection that was caused by that earlier timing. So it's coming out as like as a mathematical artifact rather. So let's see here. Okay. So yeah, that relationship holds for all the measurements. And then real quick, we can see what it would look like if the Earth were a globe. The airs would be reversed if we added the air to what we failed to account for, the initial drop over distance. It would double our air, and we would be off by the full arc length there. So that's what it would look like. So remember how Blodgett Peak, it stacked evenly and they were equal. Well, now we're off by what the drop over distance was, and then we added the drop over distance air to our measurement, and now we're double off. Now we're off by twice as much. So that's how that would look if globe on those. And let's see here. So yeah, that's a awesome find, Mike. Good stuff. Okay. So now we'll get into the uh, the recent proposal for planes occluding stars to being added to the data set and whatnot. Now, uh, I have a couple serious contentions with it. So we'll start with one of the first, and that's going to be that another observer cannot repeat that same occlusion or same elevation or same angle or achieving the same stuff. And you'll see why here in a second when we go through the possible point of errors for determining where the plane is in 3D space and how it was done by Astronomy Live. So when we see that, it would be like if Mike had proposed this method, but the mountain moved at 250 meters a second, you guys would all be like, that's a that's a ridiculous method. We're not going to use that. So it's kind of the same thing here, and we'll get into all of that. But a quick refresher on the null hypothesis as we get into all this. Remember, the purpose of this is to refute the null hypothesis. So I have mine flipped around in the way that Mike doesn't prefer it, but oops, what was that? Oh, sorry, there
Good,
was a
Alan.
uh, anyway, sorry, there was a noise outside. All right, so we have the IV control and DV here for what we put forward in the experiment. So the observer distance and elevation relative to sea level, and that determines the geometric line of sight to the peak, and that serves as the adjustable parameters for the experiment, because changing the distance to the peak is going to give you a different angle, so you'll get a different time, so you can manipulate that. The control is obviously the known elevation, so you can always come back to this peak. You might not always be able to do the same star depending on how long it is in between your measurements. If it's a couple years, it might not be coming down at the same angle or whatever. But in any case, you could still use other stars at the same peak. Extremely important. Other people could go back and verify it. And then the dependent variable is obviously going to be the occlusion angle, and that's going to be dependent on this angle here set up relative to the control. And it's an extremely important part of science, as Mike was talking about earlier, because you'll end up in an infinite regression if you don't falsify anything. You can just keep adding on things to your theory and whatnot. So it's not always important to be able to uh, to carry out an experiment to test a hypothesis, but it is important that it is possible to do that if you had to do it, because otherwise you'd also, because every time you falsify something, you could keep going down that direction too. But like I said, it's not always it's not necessarily it's not necessary to continue it, but just that it is possible. Otherwise, it's untenable, because anything that is not falsifiable is pseudoscience. It's not. If it's unfalsifiable, it's pseudoscience. It's not science. Okay, so quick refresher on the central angle theorem here. So two radii that subtend the circumference of a circle or a sphere create an arc length. So the angle between D and E here, in this case, it's going to be 50 units of degrees. And that's what creates the arc length. So how this relates to the globe model is distance and angle are synonymous. So in Pikes Peak here, instead of being 50, if it were 27 arc minutes, that distance would represent 50 kilometers over the surface here. And, and then there's another component to central angle theorem called the inscribed angle theorem. Wait, 1 second. I'm going to hit some water. So inscribed angle theorem gives us the drop over distance of the arc length. So you can find this here. The inscribed angle is always going to be half of the central angle. So in the case of 50, it would be 25. In the case of Pikes Peak, instead of for 27 arc minutes, it would be 13 arc minutes. And that represents the drop over distance of the elevation difference between D and E here. So for the case of Pikes Peak, that's going to be 200 meters, and you can convert that various ways. You can do uh, you can just arctan it and convert it over that distance. It'll give you 200 meters, or you could do a Sagitta approximation factored by 4, and that'll also give you that amount in meters. Let's see here. So that's how those relate. And then there's another important component to central angle theorem here called chord tangent theorem. So chord tangent theorem here is the difference in elevation angle between this tangent here on a sphere or a circle relative to the chord that's intersecting the arc length here between B and C. So this chord and this tangent here have an angle depression between them, and it's also proportional to half of the central angle. So the difference between a plane and a sphere is always going to be the arc length, or I'm sorry, is always going to be the inscribed angle between the arc length. So uh, what we do with the celestial theodolite is we take our measurement from the observer location here. We're recording stars getting occluded by a mountain over here, and then we check in stellarium where the star got occluded at here for the observer, where its position was relative to the peak for the observer. And then we add the arc length back. In other words, we go to the peak. So when we move to the peak, that's for the flat Earth analysis. That's what we're doing. We're traversing the arc length here. And when we traverse this arc length here, if the Earth is a globe, then if we fail to account for drop over distance, the star's position is going to be above the peak above the predicted peak angle for flat Earth by the amount of drop over distance that we failed to account for. And we see that here in the measurement where we have the idealized Pikes Peak. So if the Earth were globe, it hit that measurement, we'd be off by 13 or closer to 13. Obviously there would be like refraction, measurement error, et cetera, what have you. There would be a slight difference in there, but this is just to show what it would look like. So we would absorb all that air. The globe would have almost none of it. And then when we check at the peak, this is where the star's position would be. It would be at 244. So we would be off, because the star didn't have a chance to get lower in elevation relative to the peak. It occluded when it was aligned relative to the observer as the globe would have predicted. So that's an extremely important concept to understand, because that's how we determine whether or not there was drop over distance on the arc length, because the implication would be that on a globe, the observer is already tilted off to the horizon. Their horizon's already dropping, and they only perceive half of that horizon. The same situation applies to the star. So when you go and look at the positions of the stars in stellarium, what you could do is rewind time until, or rewind the angle for the observer until it's at 233. That'll take 2 minutes and 29 seconds. You play it out for 1 minute 15 seconds. That's 13 minutes of angular drop over that 1 minute and 15 seconds. And that's when that star will be aligned with 217 for the peak. So that's how it gets that earlier timing for their prediction, based on the geometry of central angle theorem and how what an observer would perceive on a sphere or circle based on central angle theorem. Now, there's also a Sagitta aspect to this, but like not to get confusing or whatever, but just to clarify, the Sagitta midpoint here would be the difference between the chord and the arc here, and that would be, in the case of Pikes Peak, that would be 50 meters. So you would have 50 meters obstructed from the bottom of the peak, but the overall elevation of the peak would be minus 200 meters, because that's the elevation difference between B and C as defined by the half central angle. All right. Um, so that's central angle theorem in a nutshell. Now, we're of course using the celestial sphere model. The globe uses the terrestrial sphere and the celestial sphere merged together to assert the shape of the Earth, whereas we're just using the celestial sphere, so like the same angle values for change in position over distance and whatnot. What the um, hmm, but no physical drop over distance, right? Just using, it would just be conceptual in the sky. It would be a mathematical artifact that if you were, I don't know, measuring occlusions and added the air difference to what the drop would be expected to be, and it would equal how much the globe was off by their prediction. It might have some relationship there, but who knows? So a secondary thing that was added to the spreadsheet here, and analysis, was distances on a flat Earth. A lot of people have been, you can't use a Haversine. It implies spherical excess. All these things. And sure, it does imply spherical excess. It does do all those things. And I agree that does make it very spherically appearing, right? But to illustrate the concept that it's just math, we have the celestial, instead of using the Haversine, we've changed how we derive distances now. So the Haversine formula here is what we used to use. And of course, if you do a if you check three locations, you will produce spherical excess here. So I have here mapped out the interior angles for the observer, the mountain, and a point on the North Pole. So just putting for that third piece. And if you use Haversine to derive distances based off of latitude coordinates, you will get spherical excess here. So the amount of spherical excess, oops, 1 second, the sum of the interior angles here comes out to be 12 arc minutes in this case for Pikes Peak. Now that's just coincidental to the drop over distance of it because it's very close, but it's not the relationship. It'll change for the other peaks. But for how we're computing distances, we are solving for a Euclidean triangle here. It's going to add up to 180 degrees instead of being over 180 degrees. And the math check for that is shown here under the distances. Now, this was put forward a couple of weeks ago to kind of show the equivalence between using a celestial sphere model, a celestial hemisphere model that creates a dome similar to what the exact thing that the globe lads use, but just kind of changing some parameters around and showing the equivalence there. But now we actually compute distances with spherical coordinate inputs that don't lead to spherical excess, and we achieve this by using a unit sphere. So the radius of our conceptual sphere is 1, and then we use the radial vectors. So basically taking a sweep of the sky. So if you imagine an observer here at the North Pole, and then like a line extending out that is this length here, 6,371 kilometers. That radial sweep, so the change in position of the stars as an observer moves or whatever, that angular sweep is what creates the the what do you call it, the central angle for us. So that's that's all doing the same thing. So it's using a conceptual sphere of radius 1, and then it's just using plane trig, essentially law cosines, to establish an isosceles triangle with a chord intersecting the top there, that top part there, and then that's it. That's all it is. So we don't get any spherical excess on ours when we derive the distance, and the difference in distance between the two uh, can be found here. So if there's ever any difference here, you just guys let me know. If you're cycling through peaks and you find that there's a distance discrepancy, just hit me up. So that's distances on a flat Earth. If you're using latitude and longitude coordinates and you're getting a distance output that isn't what you would normally get, then you're strawmanning your own tools essentially. So that's my thoughts on distances. We will freely use the celestial sphere, no problem. All right, now we will get into the data analysis aspect of what was put forward by Astronomy Live. Now, the biggest point of contention here, obviously, I mean, for me, this is like a complete no-go here. There's a delay in position of the information received versus where the occlusion occurred. So here we have the timestamps for the occlusion versus when the position was updated. So here there's a 2 second delay, and it's actually even worse than that. It's 2.5 seconds because there's a half second of uncompressed information that doesn't have to be accounted for. That's like their leeway in between measurements or whatever. So they don't actually have to, anyway, there's always an inherent missing half a second there. And then so for the Allegiant flight here, and we'll get into how these all add up because it might not seem like a lot or whatever, but we'll get to how all these add up here in a second. But this is essentially like not knowing the position of the mountain at the time of occlusion. Nobody would accept this standard if we presented it on our side. So 4 real seconds in position difference here at the time of occlusion. So not where it was at. And then as we keep going here, we got, what was this one? This one is a 3 seconder, and then this one comes out to be 5 seconds. Now the planes move at typical speeds of 230, 250 meters a second. And in addition to that, there's some additional information here that's provided to the on the plane side. So we have their vertical uh, so we can tell if they're ascending or descending, essentially, right? They're climbing or descending. So that's an aspect of it too. They're not even flying level over the star. Like uh, there's no way to even reproduce this, and then having a difference in position, what this leads to. So in total horizontal drift, it's not even shown for the first one, so we can't even do a difference in distance here for that one. But we have 9 meters for the vertical drift, horizontal drift for the other measurements, 860 meters, 20 meters in elevation, 800 meters in distance, 50 meters or 42 meters in elevation, 1300 meters in distance, 24 in the vertical. So that's a pretty big difference here, and we'll get into like it's not even just this, right? This is just the beginning, lads, because there was no actual air analysis done on the instruments that gives the readings that were used in the analysis. It was presented as if there was what did he say? It was 0.01 to 0.06 seconds of or degrees of accuracy or whatever in the analysis they put, but that accounted for none of the instrumental errors that occur on a plane, and we'll get into those in a second. So this is just the beginning of it, but the fact that the data doesn't even represent the position of the plane at the time of occlusion is enough for me to just be done with it on the face of it. But there's more. We'll continue. Okay. So if you were to do an air analysis based off of all of this, which we've done, we'll show the graphs first, and then we'll get into what produced these differences here. So here we have the zero line for the measurement. The air bars is this dotted line here. our measurements are within this, and then these plus or minuses here completely intersect with the errors, so you can't tell who won. Like with the discrepancy with all the discrepancies added up for the errors, you can't make it like if I were to go through these measurements and change the distance and elevate because I added them to the sheet. If I were to go through and change the distances and elevations to these to ones that were more agreeable, I could literally get them to flip and be flat Earth or closer to flat Earth, etc. So there's no meaning in this. We can't tell which is different here when you do an actual analysis on the instruments that report the positions of the plane instead of just trying to act like that's exactly where it would be. So when we get into that, we have the measurement error over the inscribed angle. So basically, it's what it's showing here is that the drop over distance, the thing that it's trying to determine the difference between this experiment, the error ends up being either equal to the drop over distance or at least half of it through all the measurements, which makes it completely useless junk data. So we'll go through here and talk about the position errors. So some of the position comes from GPS information, and there's a specific amount of accuracy threshold requirements. The FAA minimum requirement is within 92 meters of GPS positioning. Now, we gave benefit of the doubt here and used the one that's sub 30 for most commercial jets, but this is the bare minimum, and we don't even know what the planes had on them. We're just taking this for the maximum benefit of the doubt there. And then there's quantization in the encoding. So what this is doing is it's essentially rounding off latitude and longitude coordinates a little bit so that produces a small error in that. And all the sources for all these can be found here, and you can read about them. So this adds a small error there. So we input the lati and longi here, and we get we calculate what that would be as well. The uncompensated latency for the what was it, 0.6 seconds discrepancy. So literally a little more than half of a second on all the measurements being, of the uncompressed latency there. So that produces 129 to 173 meters of error. The mismatch between the occlusion timing and the updated position of the plane creates, the discrepancies for horizontal and altitude drift that we went over earlier. The altimeters also have a systemic error from flying at different altitudes. Like when you're flying through, like the air is not the same as being on a weather balloon and having your instrument read the air. Like there's a literal different compounding error that occurs at different altitudes. So they've got that accounted for in the specs here. So between 30,000 and 35,000 feet, which I think most of the flights were between these ranges here. That's going to create this error right here. So we have, let's see here, continuing on. The altitude is also quantized, and so the information that it's putting out, it rounds it to the nearest 25. So whatever the altitude is, divide by 25, and then whatever the remainder is just gets chunked off. So there's always going to be a difference there in altitude. So that adds up over, to the other stuff as well. Static source error. This is an error in the barometer, or the error in the altimeter that I was talking about earlier. That when it's versus when it's flying versus stationary. So another error there. Tool system error. I forget what this one was. Maybe 1 second. Let's see, the operations reduce vertical separation minimum. What was it citing? Budget for including instrument encoder, avionics. Instrument encoder could be off by 61. Let's see. Basic flight envelope. Right. Certification. All right, I'll have to come back to that one. I can't remember what how this specifically relates off the top of my head. It was stated, so the way that the altitude was derived was really interesting, because uh, if it was done through like the geometric GPS stuff, that would have been really heavy, or that would have been really easy to contend. But the way that Astronomy Live did it was basically taking the average of three different altitudes and then trying to relate that to the altitude that the plane was reporting at the time, but obviously not accounting for any plus or minus errors in that. But one of the things he did was use the gravitational potential height, which uses the geoid model. So there's going to be another correction for that as well, for using the geoidal altitude. So that wasn't accounted for there. So we got that in there. And then the balloons themselves have no timestamps on the data. They're launched 2 times a day. You go to the website and you click on a day, and then you click on different times over 3-hour increments throughout the day, and then you find the one that it was launched at. For I haven't done the other ones yet, but for Spirit Airlines, the one that I did, it launched 11 minutes before the time of occlusion. So the data, that's presented for the ray tracing isn't even from the time of occlusion. It would take at least like 40-30 minutes or so to ascend to the altitude to even get those readings and whatnot. And then there's also a discrepancy in the distance to the observer, and then also to the planes, for this as well. So in the balloon weather reading, game, or whatever you call it, in the industry, there's a way that they describe like the conditions that are being measured at a certain distance away from the weather balloon. So within like 200 kilometers, they call that, this one specific zone, and then anything outside of that relates to other things. So there's a whole scaling factor for all of that. And when we go through that, let's see, the observer was outside of the 200 meso, what was it called, like the mesosphere zone or whatever. So outside of that effective zone to get the necessary information. And then 2 of the planes were outside, the other 2 were pretty close. But even just given the data, because like I said earlier, when he was like first presenting this, and I kind of mentioned it last week, is that there's a computational model that's used with specific parameters. So if your conditions are close enough, you're gonna get the right value anyway. So I'm not even necessarily making such a big deal about that. But in the future, if you're gonna compare stuff like that and make it be dependent on ray tracing, you should have the appropriate measurements close to the time that it was done, or be able to show how far off in time they were, rather, if you can't have it exact. So that's one aspect of it as well. And then we have, so this Sun and Others here, cited down here, notes that there's an altitude error for weather balloons, similar to how the planes have their own altitude error when they're using their altimeters and barometers and whatnot. The weather balloon has an error every 10,000 feet or so, that that it can be off in elevation. So we took those, added that to a potential point of error to everything. And then obviously there's the mismatch from the time and position of the occlusion versus the updated data for the vertical. So we got that, not just the horizontal. And then when you add all of that together, it ends up for 19 arc minutes of air, rather than the claimed 0.0, excuse me, 0.01 to 0.06 degrees of accuracy. So between arc minutes, like 30 arc minutes or something like that, and 3 arc minutes is the claimed accuracy. But when you account for all the errors in how the machine, how it actually presents its location, you end up with 19 arc minutes of air. And I think it was 19 arc minutes of drop over distance in this one, for that first one. So it completely absorbed the difference here. 23 arc minutes of air for Allegiant flight, 42 arc minutes of air for the jet speed, and American Airlines, 20 arc minutes of air. So obviously, none of this is usable, and especially with the position of the occluding object not being at the same time as the, not even having that, even if we were to try and entertain it, just adding up the instrumental air and all that stuff also shows that it's not going to be sufficient. If we have the wiggle room to adjust things and reparameterize and, oh well maybe I disagree with using, the way that you derive the altitude, so I'm going to use this method and change it by this much, and then it's in favor of flat earth. That's no, no. We all agree on the altitude and distance to the mountains. We don't all agree on the physical location of the plane at the time of occlusion. So that's my biggest contentions to everything, and we're gonna go over this again on Thursday. So um, stay tuned for that. Now we're gonna get into the ray tracing. So it was asserted, oh, I just went out and got the local temperature and pressure from this weather balloon, and I put it in this ray tracer, and out came the globe. I didn't even assume any globe, and yada yada. Well, it's not true at all. We'll get to the ray tracing source code here in a second, but before we get to the source code, we're going to understand the parameters that were put into the source code to derive the amount of ray that had to be traced. So, to start us off here, remember I had said, um, there's a specific model that they use to calculate everything, and I'd have to take a look at the source code to see what all variables and whatnot were used. Well, nothing different was done than what has always been done. So, prior, and you can read all this here, starting with the index. There's a nice segue into everything to get into the history of all this, and then you can get to the code analysis and whatnot. But to start everything off, prior to 1939, the way that they derived the amount of astronomical refraction was assuming the air density based off of um, watching circumpolar stars at different latitudes, and then taking the position of where they were observed and comparing it to the position to where it should be, following the 60 nautical mile per degree, et cetera, et cetera, et cetera. Um, and so it was just based off of, literally what it would have to be to make the globe. Now, in 1939 here, Barrell and Sears did an interferometer experiment, and they measured the refractivity of air at the same conditions that mean sea level have. So whatever the temperature is there, I think it's 59 degrees Fahrenheit, 15 degrees Celsius, and then whatever the average humidity is. So they took an interferometer, they had a little tube, one of the arms had a tube, and it had, air in it that had that pressure and water vapor and density and all that. So they took that as their baseline for their dry air measurement, which drives the refractivity value for the model. So they took a measurement, and like an actual measurement of refractivity, to establish a baseline, and then they model it out over a sphere. Now, this is just starting with the measurement. So in 1941, after the measurement had been established, Willis comes along and he's like, hey guys, I'm going to build a model off of this measurement, because what we were doing before was just using positions of the stars, and we weren't really linking it to anything in the lab. And now that we've got some lab measurements, we can start to do some modeling. So this gentleman, obviously one of the inputs early on in his model is the globe. And the way that it sets up the model is that it starts layering out concentric circles of atmosphere surrounding the Earth, starting from, what the 0 point would be if you were an observer at the center of Earth, and then extending all the way outwards out to, I think, 80 kilometers or 20 kilometers or something like that above the surface. And so it makes that concentric rings, assuming the symmetry needed for that, and then then it uses the Snell's law to show the invariant for spherical symmetry. So in other words, like when we're looking at a curved array, it has to be symmetrical. So like for the drop over distance for Pikes Peak, for example, there would be like 100 meters of drop on one side, 100 meters on the other side, kind of thing, so it's going to arc over it. So that's the kind of symmetry that is established in the model. Now, if this model is a static model, it doesn't do well with dynamic conditions, etc. And that was one of the biggest critiques that was put forward by Garfinkel here, who we're going to get to in a second. But again, the input of this is the globe, and then unifying and linearizing a gradient essentially, and then wrapping it around a sphere. The input is the globe, and then the output is miraculously the globe, based off of a real world value there. And then Garfinkel, sorry, comes in and he's like, "Hey guys, your model is a little static, Willis. I'm going to try and add some dynamics to it." But again, he goes through the same process, put the radius is an early parameter. He ends up using a bunch of parameters that assume uh, thermal equilibrium and ideal gas law. So like there's no disturbances in the gas. It creates it's a concentric stratified circles that are like, infinitesimal circles that are just, or I'm sorry, infinitesimal stratified layers that extend radially outward. Sorry, that's a way better way to articulate it. So that's all they've been doing since the 40s here, and even before that. And then in 1966, Edelin comes along and adds a refinement to the baseline measurement of the refractivity here, but they add a coefficient that makes it compatible with the old measurement here. And then G.G. Bennett is like, "Hey, Garfinkel, your formula is really cool for predicting the refractive conditions and whatnot, but your formula is crazy. Nobody can solve it with a calculator. What I'm going to do is use some polynomials and do a curve fit to show based off of whatever angle it is, what the amount of refraction would have to be. And then, of course, you can put in temperature and pressure in here. But if you don't, it'll just default to the standard, the standard here from established by Garfinkel, or sorry, established by Barrel and Sears here for the refractivity index. And so you'll be pretty close. Like if you go to Stellarium, go to Pikes Peak, go to observer location, and don't change any atmosphere parameters, you'll get 2 degrees and like 21 arc minutes, I think it is. And if you add temperature and pressure, if you account for those in there, it goes to 219. So it adjusts it, very slightly, like, but even without those parameters, because the model is already fit symmetrically to a sphere for that, that's what it comes out to naturally. So that's what Bennett is capitalizing on here. And then if you happen to know your temperature and pressure, you add those bad boys in and you get your slight correction here. So Sitter in 1960 or 1996, sorry, came along and added an update to the measurement for water vapor. So there's two parts of the equation. There's the dry air variable, which drives the refractivity index. That assumes the air mass to refractivity proportionality. I'm sorry, air density to refractivity proportionality. And then there's also another component for the amount of humidity. So that's the water vapor. So Sitter here had an update to the amount of water vapor to add. And then, of course, there's a coefficient to link it to the original measurement. And if you run the simulation using the coefficient to link it to the old measurement or not using it, it only changes it by 10 arc seconds. So it's not really a perceptible difference. But anyway, when you take the formulas provided by Sitter, which are just these same formulas that have been already established through history of of how they would model the atmosphere, you get um, you get the exact model that they all get. Um, that's why it works. So when you go through the code, or when I went through the code here, it was all about uh, linking those original values and then showing, the one had the coefficient in it. So I ran it with and without it and stuff, and none of it actually matters. But what does occur here is, temperature and pressure are real variables. They create refraction. There's a refractivity. They measured it in a lab with an interferometer. So, not disputing the phenomenon of refraction or refractivity, etc. But so check this out though. Based on the weather balloon data, the temperature and pressure give a refractive index of 1 degree and 44 arc minutes. So almost 2 arc minutes of refraction. But wait a minute, Alan, it wasn't Pikes Peak 13 arc minutes of refraction? How did we get to 13? 13 occurs over spherical integration of the sphere. That's the purpose of having the radius in the model, to distribute this over the, symmetrically over concentric circles of the sphere relative to the arc length. When we get into the ray tracer here, what it's doing, it's taking the elevation difference between us over the arc length, and it's just literally like reiterating the same thing over and over again until it traces out the arc length and hits the observer in the eye. And then whatever refraction amount that is, that's what it has to be. And that relationship is very prevalent, because what we see in all the measurements is that the amount of refraction is almost always equal to or a little bit greater than the arc length. I'm sorry, the drop over distance itself of the arc length, making up that elevation difference based off of what, how much refraction is needed to be geometrically available, rather than how much is actually there. So within the model, where you could ray trace this out, that's how much it comes out. This is how much it would have to be to explain it. And this is the value that it's always been. This goes back to Bennett, Settleman, all using the same, types of, I'm sorry, all adhering to the same type of modeling to show, when we talk about internal consistency, this is what we're talking about. This was all built to describe this. So it turned real world conditions into 13 arc minutes of what it needed to be to describe that. So that's all this thing ever was and ever is. And you can actually go back and listen to him in the debate opener. He's describing how it works. So it's not like a secret, but it's not as clear. It's not as cut and dry as I just put in these variables and didn't assume the globe and out came the globe. It's literally bound specifically to the globe. You can find the radius value all through it. What is it? It's the ellipsoid model that they use. Yeah, everything is specifically computed with the ellipsoid model. And then when he was using the gravitational potential altitude of the weather balloon, he was using the geoid model. So that's why the geoidal difference ended up getting brought into it, because there was no compensation for that in the code. It was only referencing the ellipsoid. So there was missing one final conversion there to account for it. But in any case, the you know taking the real world conditions and integrating it over a sphere, assuming the sphere is not proof that it existed in the way that it's presented. That's just literally what it would have to be, because that's based off of integrating it over that arc length. So that doesn't really tell us anything. That just tells us what it would have to be based on those assumptive conditions and whatnot. So it's a pure model. It's not doesn't have anything to do with actual conditions. And to kind of illustrate that point, Vander Werf here and Len did a ray tracing for one of the Novaya Zemlya effects that occurred, in history. And so through their ray tracing, they got Earth's radius to go up to 38,000 kilometers to explain the measurement, where the sun was observed 10 degrees above the horizon, or I'm sorry, it was observed 4.9 degrees above the horizon when it was supposed to be 4.9 degrees below the celestial horizon. So, below the literal ball. And then it wasn't supposed to be observable for 2 more weeks. And they saw it at the 76 latitude at 4.9 degrees above the horizon. And so to ray trace that out to how it would have to work, they invoke a ducting layer that goes all the way from the whole thing right here. So anyway, that's what we're looking at here. So you can ray trace any phenomenon to fit what the globe, quote unquote, would predict, but there's no falsifiability to it, because it's literally integrating it in the model, and then that's just how much there has to be. It's not actually showing anything that's not self-referential. So you guys can go through the refractive index section here and read through all about the ray tracing and the refraction stuff. It's literally taking real world conditions and then adding like a geometric, this is what it would be geometrically if X, Y, and Z were true. And It's not proof of anything. So those are the updates that we have for the ray tracing and for the analysis on the planes. Any questions about any of that so far?
What formula did he actually use to calculate the actual ray curving for the segments?
What formula did he use for the actual ray curving? Let's see. Let's see here. So we got the input parameters. These are all the refractivity of the dry air stuff from that I was talking about from 1913. I'll link back to that. There's the water vapor. Here's the 1.022 coefficient to link the new water vapor to the old. But like I said, if you remove this, it changes it by 10 arc seconds. The final air density as computed by the values put in here is this. So there's part of it. And let's see. Let's see where R enters the ray tracer. So line 162 to 163. So there's the radius, the WGS 84 model on line 362. We have the normal section radius behavior for lat long. So this is giving the starting to computate the peak value, or I'm sorry, the elevation difference between us, or between peak and observer here, so that they could do the integration. Spherical Snell's law. So what we talked about earlier with the concentric shelled layer of atmosphere. This is all of this. This B parameter already has the radius cooked into it, and then now it's going. Oh, it's like this is like the reiteration process where it's the refraction index times the radius. So it's just reiterating the same arc length until it intersects with the observer. Here's more of that going around. Central angle to the target. Let's see. Yeah, all in there. So,
Seems like celestial theodolites unrefuted. Balloons didn't work.
I've got a brief question, one for Alan and one for Dr. Mike. So Alan, in your geometric drawing of this solution, where would you put the star? Where is it physically?
sorry, wherever you perceive it angularly.
No, where is it physically? Where would you put the star in your drawing? So it's directly above the GP at the time of the observation. Is that correct?
Directly above the GP at the time. What are you saying again? Sorry.
So at the time of the occlusion that you're observing, the star is physically above the GP of some other observer, right?
Oh, got you. Yeah. So
where is that? Where is that location?
Yeah, so that would be 9,774 meters away. The GP referenced is a calculated position of where it would be using, the coordinate system itself, and everyone agrees that that's where it would be. There's no one there to actually measure or confirm that that's where the zenith position of the star was at the time of occlusion.
Then we can precisely predict those times of occlusion, times of zenith, right? So what if the angle was steeper and the GP was, say, 500 miles away?
Well, one second. You just said that we could predict the zenith timing, but as I just said, no one's ever measured the zenith timing. So anything that follows that is, you're assuming that that's true, right? It's never been it's never been measured. It's an agreed upon position of where it would hypothetically be with respect to a fictitious observer at the center of Earth. So whether or not it actually has a GP there is irrelevant. People agree to it and calculate things based off of where it would be there. That's my position on it. Where it actually resides in three-dimensional space, couldn't tell you. But where it resides within the coordinate system, that's self-referential. It would be 9,774 million meters away.
Well, that depends, right, on the angle you're observing it at.
Sure.
and that's where your so assuming that you could measure those distances along the ground between you and the GP of the star at the time, that's where your distance is going to break down rather badly, right?
No,
Be off.
no, of course not. We're literally, did you see that we're using a unit sphere of radius 1 and a
Yeah.
radial
But
vector cross
you're working
product?
out the chord using the chord length when you
Okay.
do that, right?
So let me put in a distance here of
So
nine.
chord length over
Yeah,
9,000 meters is going to be tens of kilometers out,
let's
at least.
see. Let's see. Let's see what happens. Here we go. 9,700,000. You ready?
Sorry, I'm having trouble with your stream.
Oh wait, why didn't that update? 1 second. Oh, because it's between latitude and longitude. I'd have to change the latitude and longitude. 1 second. Let's see. See if we can have 1 second. Let me see if we can have ChatGPT generate latitude coordinates that are 9 million meters apart. Generate lat long coordinates for two observers 9 million meters apart. All right. Let's see what happens here.
Yeah. So you're 9,000 kilometers. You're basically saying that's 1/4 of the circumference, right? 90 degrees.
Uh-huh. Okay, so if we did 0, 0, 0, 0, 0, and we did latitude 0, 0, longitude 0, 0. We said distance test. Oh, I think we need a star. No, didn't. Oh, wait, I know why. Didn't put in the distance formula. There we go. 9 million meters, 9 million. All right, let's check. Identical.
What? Haversine distance and the chord distance.
Haversine distance produced the same output as the triangle that adds up to 180 degrees. You see it right here. So there's no breakdown, there's no nothing. It's
So
a literal. Go ahead.
I think you've made an error. So if you've got a triangle
Mm-hmm.
with two arms, radius r, and you
Mm-hmm.
work out the distance between the two ends of the triangle, which is the chord length, right?
Mm-hmm.
The chord length has to be different than the Haversine formula because the Haversine formula is the arc length across the surface.
I look forward to you pointing out the error.
Okay. I'll do that for you
I
later.
please do. Please.
And the other questions for Dr. Mike, if he's listening, I'm not sure whether he's able to or not. Just thinking about his presentation earlier, and experiments, and particularly his experience in the satellite industry. I'm wondering whether he thinks it would be feasible for amateurs to measure the ephemeris of a satellite themselves, and if they could, what would that ephemeris look like over a flat Earth?
You're asking a question that my existing non-disclosure agreement prevents me from discussing.
Newton
Okay.
would not want that disclosed.
Yeah. Newton and Doppler would be very upset. Okay. So I'll try and narrow it down to things that are public domain. is it feasible that an individual could measure the ephemeris?
Is that question directed towards
Oh,
me
yes,
again?
yes, yes. Sorry, Mike. Yes, yes. So, is it feasible that as an individual I could determine the ephemeris of a satellite myself?
I Could you explain in what context you think this is relevant?
Just the context of the shape of the Earth, actually. So we have one experiment here determining the shape of the Earth, and to understand the ephemeris of a satellite might give us other information about the shape of the Earth, like they did with Sputnik, right? They learned a lot about the oblateness of the Earth by observing the Sputnik orbit.
So
Yeah.
are you
So
aware of what ephemeris characterizes for a satellite? I mean, basically what you're saying is, can somebody calculate something that's placed on the globe Earth? And then in what context is that relevant?
Oh no, I would like to create an ephemeris relative to my position on the Earth. So I'd like to observe a satellite and uh, work out its geometric path through the sky.
So how you would calculate such theoretical ephemeris would be based on the shape of the Earth. And when you start talking about ephemeris for satellites, that's a topic I can't discuss.
That's all right. But I don't need to use the shape of the Earth, right? I can just measure the position relative to where I am and track its position through the sky and work out what its path is. At least during the visibility of it to me, I could work out what its path is.
What does
So
this
would
have
you
to
walk
do with the
through how you would
presentation?
stat?
so yeah, do you like we're it's like so like what's
Oh,
the
I was just in.
what's the end game here? Do you want to use the thing that's going to be self-referential to the coordinate system itself and not talk about the geometric intersections using an independent reference, otherwise known as a mountain? Like,
This
can we
is a
talk about
geometric
that?
solution,
Can
Alan.
we talk about you know what else is a geometric solution? The occlusion angles at the time of occlusion. Like when we add the arc
No,
length
it's not a
back and
geometric
check,
solution because you don't
yeah.
have the geometry of
Well,
the star. You can,
if you're gonna just like immediately talk over me, like obviously you're just gonna get your volume turned down to zero, and then I'm just gonna talk over you, and then nobody gets to really hear anything.
You're breaking up, Alan.
So that's not going to be beneficial
If
to
I could
anyone.
jump in while he's breaking up, I would take you back to the null hypothesis, because the problem with what you're attempting, the direction you're trying to take this conversation, is you're starting to make a lot of assumptions, all debatable. And that's why we use the null hypothesis to refute the one thing that cannot be if all of your assumptions are correct. So if the Earth is the shape you believe it to be, and the ephemeris means what you believe it to mean, and you make your calculations, one thing those calculations cannot prove, or the hypothesis that the Earth is a globe to be correct, is they can't disclose that the Earth is flat. And what we are finding when we make these measurements, we assume that the Earth is flat, and our only challenge is to refute that. But every time we try to refute it, we find out, yes, indeed, this verifies that the Earth is flat.
and who has the true angle to the star?
So, so for
That's a
the answer
great
to that,
yeah, that's a great question because there's the angle that you see apparently, and there's the angle that it's compared to for the linearized version uh, to maintain the 60 nautical miles per degree using a fictitious observer at the center of Earth to make both models viable. So it doesn't really matter where the position of the star is in 3D space. It matters where the occlusion time happens because that's when whatever the light source is relative to you is blocked by something. And there's two different mutually exclusive timings in which said star would be blocked on a flat Earth versus a globe. And every single time, Flat Earth Rise Over Run makes the prediction with no assumption other than the Earth is a flat baseline. The globe gets three corrections. They get one correction to make their baseline curved, to deviate from a plane. Then they want to introduce another correction to add that curvature back in. And then they also want to add in a terrestrial correction just for good measure. So that's what we're talking about here, the celestial theodolite. You're diverging the conversation into something that's not relevant to falsifying the null hypothesis.
So so there's zero refraction involved in your observation. Is that what we're saying?
We're
And
saying
your
that
calculation.
not accounting for anything and just going on the raw geometrics. Our premise is that geometric intersections are when the light source has been occluded, by a physical object. So we see the apparent position. The occlusion happened 2 minutes earlier. Our position is that the linear 60 nautical miles per degree isn't being followed. This is a deviation from the conceptual model.
So what's your expectation then? If I was to walk down the path, follow the line, well, if I had 1,000 friends, I got them to sit along that line of sight because we know the occlusion is going to happen, right? We get them all to line up, and we get them all to be known distances away, because we know we can calculate the distance, right? Because you use the distance calculation there. We can calculate the distance along that line of sight.
Yes.
Whose angle is the one we should choose to look at the star?
Oh, everyone's going to see the occlusion at a different time based on their relative angle to it and distance away.
Yeah. So how can we predict the angle from the time of the occlusion? So you guys know when the occlusion is going to happen. Well, no, you know when the angle is going to be there. So how do we predict the angles of observation for all the other people?
Based off of their distance and elevation difference to the mountain peak, same as you did the first guy.
So why does the apparent angle not align with the triangle that you've drawn then? So if we extend your triangle and you're drawing out to the GP, put the star directly above at the end of the triangle, so close the triangle off, why does everybody along that baseline get an angle that disagrees with your triangle?
Because they're at a different distance.
No, but even if they are, so if they're walking along the baseline of your flat triangle and measuring the angle with distance, why is the rate of change of the angle not the same as your triangle predicts?
I don't even know what you're saying at this point right now.
What I'm saying is that why doesn't your triangle predict 1 degree per 60 nautical miles?
Dude, what the freak are you talking about?
If you go along your flat baseline triangle, which is your geometric model of the Earth, for every nautical mile I move towards the GP of the star, the elevation, for every 60 nautical miles, the elevation angle will increase by 1 degree, right?
How are you this confused in the conversation? This is exactly what there's no difference in. This is representing 1 degree of 1 degree per nautical mile here. This is what all this comes out to, the same exact thing. This is how we're able to direct. Okay, dude, as we're looking at a spreadsheet that has all the math for it, go ahead and look through it and present that it's not that then. Here's the link, man. Enjoy. You're going to sit there and say, no, it's not. Make this wild accusation about how that doesn't add up. You're looking at it be the exact same. Like so that was your, hold on a second. Your whole point to get back to that was nothing. Just to be clear. It was to be clear, your point was 60 nautical miles per degree only works on a globe. Buddy, if that were true, these occlusions would be completely different. You can't come here and just rigmarole argue out of nothing, bro. That's a waste of time. If you hold on a second, I'll let you go in a second. But just if you want to validly critique this, here's all the math for it. Go through it. Find me the error, dude. Good.
So I'll say it again. So as we can demonstrate this, right? So as I traverse along the line of sight that is the baseline of your triangle, the angle to the star will increase by 1 degree for every 60 nautical miles. That does not align with what your triangle shows.
How do you know that? Did you look at the spreadsheet, or are you just willy-nilly saying shit?
Daza.
Because it's a base.
Okay, buddy, look at the spreadsheet. Tell me where it's wrong. Otherwise, you don't have an actual point. You're just saying, oh, 60 nautical miles per degree can't work on a flat Earth. Well, it doesn't work on a globe either. As it gets lower to the horizon, as it turns out, the stars don't follow that relationship. They start to deviate.
at the last single degree of descent here, right? What about the other 89 degrees between zenith and the horizon? Can your model
Yes, it's all in the spreadsheet that you haven't looked at and are saying that it's not, doesn't work, etc. Does anyone have any questions or comments or concerns that isn't DAZA?
Yeah, I have a question. Mike initially started off by saying that he used the true position of the star for occlusion timing. My question is, why would you use for Dr. Mike, why would you use the true position of the star and not the apparent position for occlusions?
And that's because to refute the null hypothesis, the null hypothesis is basically the flat Earth position, that there should be a straight line of sight from the observer to the star. And when it's intersected by the peak, it's the peak that stopped it. And therefore, the angle of the star at the peak at the time of the inclusion, the one angle it cannot possibly be is the angle that's calculated for the observer. And the angle calculated for the observer is the true position of the star. That's why we use the true position of the star. And I've gone a little farther since then as I realized more what's going on. And that's when I realized it doesn't matter whether you take the true position of the star at the mountain or the true position of the star at the observer. The only difference between those is the central angle. So you add the central angle to the elevation stellarium says the true position of the star for the observer, and you end up with the flat Earth angle every time.
Okay, so
Uh,
do you think that when you go out and see stars, do you see the true position of the stars? When just not talking about inclusions, but when you go out close to the horizon, like at 2 degrees, do you see the true position of the stars?
Not necessarily, but that's not really an issue here. The issue is refuting the null hypothesis. So if the hypothesis that the Earth is flat is false, that you should be able to refute the fact that mountain peaks occlude those stars at the flat Earth angle, and that's what our globe Earth friends are failing to refute.
So if you don't actually see if you don't actually see the true position of the stars at 2 degrees, then why would you expect to see the occlusion of peaks by peaks at the true position?
I'm not sure I understood that question. Peaks by peaks. Have we changed to a different hypothetical?
Nope. You're timing occlusions by mountain peaks. So if we don't actually see the true position of the stars near the horizon, within 5 degrees, then why would you expect to see an occlusion of a star at its actual position if we don't actually see where the stars' actual positions are?
So you're making an assumption that we don't see the actual position within 5 degrees, and the evidence shows that we are pretty darn close to the actual position down to, I think, in the neighborhood of 1 degree. After
One
one
degree
degree,
out
it
of
becomes.
Sorry, 1 degree out of 5 degrees is precise enough for this.
Testing 1, 2. Did I lag out? Yeah, I did.
So you
It's
said
way off. But there,
you
wait, before you
oh,
interrupt
sorry.
me, let me finish answering the question.
Yeah, I thought you
On
paused.
that
Sorry.
plateau, the globe Earth says that star is 12 degrees below the horizon. So in other words, there needs to be almost I'm going from memory, so I may get these numbers right, but if I recall right, it's almost an entire degree of lift due to refraction that the globe Earth needs to even explain why the star is occluding at that point. Well, that was my last statement on my presentation. That was due to a mistake I made because I discounted the effect of refraction to lift that star, but I failed to account for the fact of what flat earthers believe because I wasn't the flat earther when I proposed this experiment. That the stars are rotating toward the horizon, not descending under it. And that's what
Okay, so
accounts for the entire.
all right, sorry, I didn't mean to interrupt you. You paused. So do you want you can finish.
Oh no, that was the end of it.
Okay.
So
So you admitted, well, I thought you admitted early when I first asked you that we don't actually see the true position of the stars. Is that correct or incorrect?
no, you are speculating based on misinformation.
Well,
What I told you is that the stars appear to be pretty accurate indicators until they get down to 1 degree. And I believe the only 1 degree mountain in our data set is North Peak and Greenhorn Mountain. And there's a big error there due to not accounting for the stars rotating toward the horizon on a flat Earth. But there's an even bigger error assuming that the stars rotate under a globe Earth. So they're both wrong. If the globe Earth is wrong because refraction wasn't included, the flat Earth is wrong because it doesn't account for the fact that stars are rotating toward the horizon rather than descending linearly when they get to such low altitudes.
okay. So at those low altitudes, like 3 degrees or less, is our observations of the positions of the stars more consistent with stellarium when refraction is turned off or turned on, or have you done that analysis?
So there again, your that was misinformation you provided. I've said many times it doesn't become nonlinear until it reaches about 1 degree. So at 3 degrees, it's still linear enough that we give good results. Yes, we've endlessly done these comparisons with refraction on and refraction off. The globe Earth is always wrong. The globe with refraction off, globe Earth is always wrong by the exact amount they predict to be the drop of the Earth due to its curvature. So we know for a fact the globe model uh, fails to meet their basic premise, and that it deviates from the flat Earth measurement by exactly what they predict to be globe drop.
So you keep deflecting from my question. I'll ask it. Sorry, I'll ask it a little bit simpler. Maybe I'm not being very concise. So
Wait a minute.
my
Before you ask it, tell me what the
that
deflection is.
why it does, do our observations, not talking about occultations, but do our observations below 5 degrees? Do our observations more of star elevation, do they more match stellarium with refraction turned on or turned off?
Okay, you wouldn't explain what the deflection is, but I think from the way you phrased the question this time, I understand what you're
Okay,
saying.
great.
And what you're saying is, why don't celestial measurements agree with terrestrial measurements? But that was the
No,
very
no, that's not
problem
my
that I found
question.
at the beginning.
That's
Okay,
not
then
my
explain
question.
it more thoroughly what your question.
Yeah, sure. I'll do it real thoroughly. Do our observation of stars, do our observations and angle measurements of stars, angular elevation measurements of stars below 5 degrees more accurately match stellarium with refraction turned on or turned off?
Are you talking about celestial measurements?
Yep. The angle of elevation to stars below 5 degrees, do they more accurately match stellarium with refraction turned on or turned off?
Okay, now that's a different
So,
question.
so,
That's a
so,
simple question,
so,
right?
so
That's a
real
simple
quick,
question.
different question entirely, and here's why.
No.
Because sometimes the angle it does make it basically what the flat Earth angle is. So for Pikes Peak, for example, we have
You're
we're t-
deflecting.
You know, well,
Just answer the
I'm
question.
about to answer you in full, bro. I just said sometimes it does,
Okay.
but we're going to get into some real specifics on this refraction scenario to really hammer it in to show why we don't really give a shit about what the astronomical refraction is, irrespective of the fact that we just went over the real world conditions get taken and integrated over a sphere based on the arc length to produce whatever it has to be to describe it. So, so your question is it more closer to what flat Earth predicts? It makes them pretty much identical almost in most cases.
Nope, that's not the question. Hold
No,
on, let me ask
it
the
is.
question one
Your
more
question,
time.
hold on, no. Hold on. Your question was, is it closer than what flat Earth predicts, the apparent position? I'm about to show you in great detail, in which nobody ever addresses or recovers from, and they just simply restate, oh, but isn't it closer though? The reason why it's closer, why it's recovering that drop over distance of the arc length and matching flat Earth is because it's integrating over a sphere and compensating for the elevation difference of the arc length. That's exactly what's happening. So when we look at Pikes Peak, for example, we have, excuse me 1 second. For Pikes Peak, we have 13 arc minutes of refraction. The drop over distance, the half gamma is 13 arc minutes. Add those together. Oh, look at that. The flat Earth time and the globe Earth time are pretty close. Now, the globe is predicting uh, 13 arc minutes of refraction. They missed their intersection by 17. So what always ends up happening is the globe lads just cut this 2 arc minutes of refraction out, and they're like, oh, it just so happened to match, uh, 11 arc minutes of refraction and not really 17, even though earlier everyone was so gleefully joyous at how calculating this amount of refraction with real world variables, confirms this, even though not realizing that it was integrated over a sphere to give that exact distribution of what it would have to be. They're just going to go ahead and cut off the amount that was computed instead of using the amount that would be said to be there if there was no mountain. Okay. Now, in addition, so keep in mind, we're going to look at 2 components here, not just the raw geometric intersection. We're also going to look at the apparent mountain peak, because a lot of the globe lads would like to raise the elevation of the mountain peak so that the refracted image blocks the apparent starlight and what have you. So we're going to look at that too. Okay, we add 2 arc minutes to the terrestrial refraction for Pikes Peak. We get 7 arc seconds in difference. So pretty close match there. So 2 corrections coming in to match. Or is anyone impressed yet? Not me. We're going to go to Blodgett Peak now. Arc length 9 arc minutes. The drop over distance here is 100 meters. The refraction was 17 arc minutes, they're claiming. Almost 3 arc minutes have to get cut off to just match the raw flat Earth angle there. And then that obviously creates a timing difference that, oh, look, with the correction and cutting it off to match the actual occlusion, you guys get you guys get close again. Oh my God, no way. So after adding out what was drop over distance back, you're close to the flat Earth angle. That has no meaning whatsoever, especially when you consider how it's computed just through integrating it over a sphere. In every scenario, the arc length gets traversed more than what is predicted by the globe Earth, even with refraction. Now, one real in particular one that I want to go over, and then we'll wrap it up, and you can respond or say whatever you want to say, is North Peak. North Peak is really interesting because the true geometric position of the star is said to be below the celestial.
Alan, they're
Yeah.
trying to speak over you.
Oh,
I guess you have them muted.
yeah. Let me just mute them real quick. Let me finish this out. So, for North Peak here, it's 12 arc minutes below the celestial equator. They have 24 arc minutes of refraction. Over the arc length, that converts to 928 meters of lift. There's 1,300 meters of drop. It doesn't compensate for it at all in that regard. So for this measurement here, for the raw intersections, the apparent position ends up being 3 arc minutes above the peak, meaning it should have to linger and set into the peak for another 46 seconds. That doesn't happen. If you add the terrestrial refraction value to the peak's elevation, then the star ends up being 2 arc minutes below the peak. It would have already been occluded by 30 seconds ago. None of these things ever happen. So the fact that sometimes they're similar and what have you isn't a product of reality. It's literally adding back as much arc length as needed to, I'm sorry, it's literally removing as much drop over distance as what's needed to compensate for the measurement. So go
Alan,
ahead.
you're lagging again.
Okay. Can you hear me now?
Could I ask Dr. Mike a question while Alan sorts his internet?
Testing 1, 2.
Oh, thanks. Dr. Mike, are you there? Oh, excellent. How much non-flatness would the celestial theodolite have to measure in order to refute the null hypothesis?
Equation that deals with the distribution of the variances.
Sir, yeah, disconnected from Discord, trying to reconnect here. My internet's just having a tough time tonight.
On Pikes Peak, that just happened to immediately tell us, oh, this is a flat Earth angle. There's no question about it. What we discovered as we went to lower and lower peaks, which kind of violates what we were going for, but the lower we go, the closer flat Earth and globe Earth get in their predictions. And the reason for that is ultimately you reach the point in the globe Earth angle in the globe Earth prediction where alleged refraction becomes a significant factor. Similarly, in the flat Earth in the flat Earth view, which I didn't completely understand when I began this, since I wasn't a flat earther at the time, the stars rotating toward the horizon also start making the angle nonlinear. So one of the things we're going to have to do is we're going to have to come up with a flat Earth correction for low angles, just like the globe Earth correction for low angles. But unlike globe Earth, it won't be refraction. It'll just be linear, not based on temperature, pressure, any of that stuff. In fact, what I've discovered is based on the altitude of the mountain and the distance from the mountain. And it'll be a while. We're going to have to go through a lot of peer review before we're ready to present that. But there's a clear relationship that doesn't constantly change, like refraction is constantly changing, that predicts the angle much closer every time.
So it sounds like at this point, without definable criteria for falsification, it is unfalsifiable, right?
Absolutely not, dude.
No, not at all.
Absolutely
All
not.
you have
Hold
to
on
do
one
is look at the
second.
graph
Can you
and
hear me?
see.
Am I lagging still?
You're good, Alan.
Yeah, absolutely not. And you asked this question of me a couple of weeks ago and I answered it. You keep like asking it to try and get different answers or some shit so you could say that it's, not falsifiable. I told you specifically if these errors were reversed, the Earth would be a globe. That's how much flatness would have to not be measured for it to be a globe. All of these would be reversed. If we added the drop over distance to the air and it added to it rather than canceling out, then that would indicate that the Earth is a globe. So there is falsifiable criteria here. It's just like, did you forget, or did you want to ask Mike to see, or John, or you're trying to ask Mike to see if you could trip him up, or like, what's the goal here? Because there's no actual way to falsify this refraction value that gets geometrically integrated over a sphere of an assumed radius, taking actual temperature and pressure. There's no way to falsify that. How much refraction is too much refraction? How would you even test it? None of these questions are questions that are answered by any of the globe lads anytime ever. But every week we come here and show the geometric analysis, and everyone wants to talk about what the globe would hypothetically predict if their spherical integration of actual temperature and pressure measurements was correct. Then that would mean that the Earth is geometrically flat and the globe is an optical correction. So, do we have any answers for how it would be falsifiable? Obviously, it would be different if the geometric intersections were reversed. That's it. The criteria that we use every week to assert the flatness, if it were reversed, would mean that the Earth is a globe. Is that clear enough?
Yeah, I recognize that you fabricated a globe error, no globe, in order to make the globe error larger.
Yeah, it's from a specific theorem called chord tangent theorem. I didn't fabricate anything. It's the geometric relationship over the arc length. You just say wild things and hope that nobody understands what you're talking about. It's not a globe error. If it's a manufactured error between the positions of the stars over two positions and where the predictions for the intersections are, how could I possibly have manufactured that? Go ahead.
By choosing a method to put in your H13 cell that no glober supports because it does not reflect reality, how globers see it.
I don't care if no globers see it that way. When you guys make predictions for when the sun set, for other celestial phenomenon, etc., it's all relative to some geometric intersection point. For you to add refraction to have there to be a deviation from, there has to be this intersection difference. So this whole idea of no glober may accept it, that part might be true, but I didn't manufacture anything. It's a literal geometric difference between the two models and the measurements.
So, you're not disagreeing with central angle theorem, just the application of it. Is that correct?
It's worse than just that. It doesn't
Okay.
have anything to do with that. He's putting stellarium at the observer location with atmosphere turned off, and then taking the difference between that and the true occlusion, which is with refraction according to the globe model, and then saying, look, there's this huge error. If he corrected for refraction correctly, then there would not be that huge error.
Ooh, so there's where you're wrong, big dog. There's no, you're not referencing a true occlusion. You would be referencing an apparent occlusion with your apparent angle with your refracted position. So you missed your geometric intersection for the true intersection, as noted by this difference here, which is supported by Euclid and the boys, as we've been over before. So this isn't a straw man of the globe. You disagree with the refraction amount, which we already went over, is spherically integrated over a sphere and can't be falsified. It's self-consistent with the model, assuming symmetry. So there's nothing in this that tells me, oh yeah, there must have really been this much of refraction. It's always the amount that is the drop over distance of the arc length. Oh, no way.
Well, you and I disagree on whether the star, mountain, and observer are in a geometrically straight conjunction at the time that the occlusion is observed. So we'll have to sort that out later. I do have one
Oh,
more
we could
question.
sort it out right now. All of the measurements when we add the arc length back show that we recover the flat Earth angle. So you can disagree with it, but the data is there showing every single measurement with that. And then adding two corrections, you want to say that it can sometimes be closer. All right, dude.
I mean, that's no different than starting with, flat Earth and correcting and recovering the globe angle. I mean, it's like, yeah, the difference between flat and globe is the curve difference between flat and globe.
It's entirely different because if we add the arc length back, we should be off in elevation by the drop over distance that we didn't account for, which is shown here. The elevation of the star would be 244 at the time of occlusion, not 230, because we failed to account for the 13 arc minutes of drop. So if it occluded at 217 for the observer as predicted by the globe, for the observer-centric prediction for the intersection for the baseline of the prediction to begin to even add the refraction for there to be a difference from, we would get, hold on, we would get 244. Okay. So adding the arc length back to check is not the same as adding a fucking correction to say this is the difference in the measurement. We're literally checking the position, not adding a correction to it. We can't use the observer-centric position because it's already a curved baseline. We have to add the arc length back and check the position as per chord tangent theorem. And if chord tangent theorem holds, which, proven by Euclid and the boys, these for flat Earth, when we add that back, we should be looking at a star that's at 244 at the peak for the true position. Never is. That would hold for all the measurements, that relationship. It's not the same thing at all. It's completely different.
I did have another question for Dr. Mike, if I may.
Oh, you're right, Alan. You're right, Alan. That is completely different. What were you going to say, Brian?
Can we go back to Wesley's question? There's a severe misunderstanding happening. All of Dr. Mike's occlusion angles are from the peak, and Wesley is thinking in terms of the observer. So if you're talking about from the peak, the true angle will more closely correspond to the star. And if you're talking about the observer, the refracted angle will more closely correspond, and that has to do with the lingering effect of the star, which the refraction is approximating.
Or with atmosphere off.
Mike or Shane or Biasicles, if Alan's not there, I mean, you guys can answer that.
Sorry, I'm back.
I believe I just did answer that.
So again, the question, Alan.
So what was the answer? What was the answer? On or off?
If you're talking about from the peak, which is what Dr. Mike is talking about,
No,
it's off.
No, you're missing the question again. The question is when we observe a star, when I observe a star, and I've at some elevation, is the elevation of that star that I observe, is it closer to what stellarium tells me is the geometric, the unrefracted, the atmosphere off angle, or is it closer to the angle that it tells me with atmosphere on? That's the question.
The question was, with atmosphere on, it can be closer sometimes, but we went over the implication of trying to use it for consistency, and it never shows consistency in terms of like this value says that it's 213, so there should be an additional 2 arc minutes of waiting for the star to fully set into the peak. That never occurs. There's scenarios where it ends up being under the peak or over the peak, depending on which type of refraction correction is used. And
Okay,
on top of that, real quick, John, real quick before I wrap up, remember, guys, never forget this. The amount of refraction that's actually present is spherically integrated over the arc length. There's no way to falsify it. Go ahead.
Okay, so you said it is sometimes closer with atmosphere on. It's my impression that stellarium routinely gives predictions that are closer to what we actually observe with atmosphere on, because after all, that's what people use it for. Are you saying that's not true?
I'm not saying that's not true, but what I am saying
that's all I
is that when we do a geometric analysis for occlusion predictions, the globe is apparent and it uses a correction that's literally integrated over the arc length, providing the elevation difference of said arc length exactly. When we go through the refraction corrections and we look at the relationship to the half arc length, which is the drop over distance of the arc length, we see that in pretty much every scenario, the refraction has, compensated for the drop over distance of the arc length and added some additional. So there's no consistency to it at all. All this is just saying, hey, that arc length there is actually flat. And then anything bonus we hope we can compensate for. And so when you're chopping off the amount of refraction that's left over in the measurements to match our angle, all you're doing is just recovering the flat Earth angle of the arc length, which is not what the globe should be. It should be reversed. We should be off by that arc length. I mean,
I'm sorry,
just to be clear. Go ahead.
So yeah, just to be clear, you said you're not saying that isn't true, but I think it's a little easier than that. The question is simple. Is the angle that we actually observe closer to what Stellarium reports with atmosphere on or with atmosphere off?
I
And
got you.
I think the answer is it's always closer with the atmosphere on. That's what the atmosphere is for in
John,
Stellarium, is
follow-up
to do that.
question.
Is that not
Is
true? I mean, it's just
it
yes or no. Isn't that true?
follow-up question? Yes, and I just explained
Okay,
why.
thank you.
And I just explained why though, John. It's integrating it over the arc length. It's fully compensating for it. There's no way to
So it's
distinguish.
accurate.
87% force fitting a
No.
sphere is not accurate.
No. Like that's the thing. No.
It's where it says it is. We see it where it says it is. Why don't you use that?
One, we're doing occlusion predictions based off of geometric intersections. When a
we see it. Where we see it.
Yes.
Okay,
And
cool.
where we see it, we're going to have to do some analysis because some people think we live on a globe. The coordinate system is tied to what's considered to be the globe. So we can't just use where we see it. That's what's in contention. If there was hypothetically a spherical integration of atmospheric values over any arc length, then it would fully compensate for the drop of the arc length. And that's exactly what we observe. And we observe even excess in that, and even scenarios like North Peak where it failed to even compensate for it, and then even contradicts the apparent elevation of the peak. No one ever comments on that. Everyone just wants to recycle back to the rhetoric of, if we take out the arc length via a refraction correction that's spherically integrated over the arc length, we can say that it's closer. Guys, that's unfalsifiable, for one. Two, it's assuming your model is correct because you're integrating it over a sphere with a specific radius, not testing anything. Okay, the geometric analysis is what shows the cause of the occlusion. These numbers should be reversed, not.
Alan, I have
So
I have one more question, which I was going to wait until after Jesse, if he will
Before
indulge me.
before you
this
ask
is
the
perfect.
question,
Okay.
before you ask
Yeah,
the question, answer my question. Are the atmospheric conditions spherically integrated over a sphere?
Yes.
Okay, fantastic.
And they're accurate.
Okay, so can I
hold on
ask,
one second.
Can I ask
And
one more?
hang on one second. The adding and they're accurate, buddy. They're integrating it over the sphere that they're assuming. It wouldn't not be accurate. Saying that it's accurate over it is retarded. It's assuming that it's accurate.
You're comparing the model to the model, and he doesn't even realize it. It's like, yeah, I see, but it's right.
That's
right.
so
where we
that's
see it is.
that's so insane.
No,
So
it
you're
matches empirical.
so then you're arguing for an apparent globe, not a geometric one.
Okay, but then why would you use something that we don't see? Why would you use a model that we don't see?
Let me ask my I have a very simple question, and then I will shut up and go away. And it really,
I'm going to hold you to that. Go ahead. Real quick, get that question out.
Oh, okay. You're asking Daza?
Quickly.
Me? Oh, Daza. Okay.
No, you. You said you had a question, and after you answered it, you would leave.
It's very simple. I intended it for Dr. Mike.
Ask it quickly, brother. I don't need prefaces. You said you would leave if I answered it, John. Don't tease me.
Okay. So it's always about, I put a thing in the chat.
Jesus Christ. What's the question, John?
It's about, okay, it's not that. It will take me.
All right, John. I'm out of time.
Yeah, dude, he said simple, and then he fucking prefaces it for 5 minutes. Holy crap.
What is the next question that anyone has?
QOP
QOP
has a question. If you could be unmuted, QOP has a question.
Absolutely.
And then I have one after him, if I may.
No way. You guys got the balls to debate me on this?
Did you have a question?
All right. So, do you claim? Wow, this is crazy. I didn't think you were going to unmute me. So you guys claim the globe mountain should be lower, right? Is lower?
Mm-hmm.
Okay. Even though the globe model is reverse engineered to where we see the mountain?
Yeah.
So we see the mountain in the same place?
Optically, yeah, we see it at what the globe would predict.
So if we see in the same place, how could the mountain on the globe be different? altitude.
How could the mountain on the globe be different? What is your? I don't understand what you're asking. No one's saying that the mountain's different on a globe. What do you mean?
Yeah, you guys are saying there you're comparing two geometric positions, one flat Earth mountain higher than the globe Earth mountain.
Mm. Yeah, when we compare the geometric intersections over that arc length, it makes the flat Earth angle, and it should make an angle that's too big by the amount of Earth curvature that we didn't account for.
Okay, so you're like avoiding my question. You guys are differentiating. You're comparing. You're claiming you can prove one or the other, and they're different elevation angles to the mountain on each model, right?
Mm-hmm.
Okay, so how does the globe have a lower mountain if it's reverse engineered from what we see optically?
That's exactly why it's lower. They're asserting that that's a physical elevation, though, and when we
It
compare
doesn't matter if they assert it's physical. They
what
see it in the same position.
No, it matters entirely because when we compare the geometric intersections at the time of occlusion, that's what would be the elevation difference. The elevation differences over that arc length. So if the Earth were a globe, the occlusions would occur closer to their geometric angle, but it never does. It
You're
always
just claiming because of
traverses.
the occlusion timing is changes, which is obviously just an optical phenomenon, like anything with surveying. The optics is going to change of the day. So you're just claiming, without any reason, the mountain on the globe would be lower, and so um, you guys choose basically for wherever you know. So
The
on your
globe,
website, doesn't it on
the
your
globe has
website
drop
on your
over
website
distance queue up.
So you're
So
claiming the mountain for the globe should be lower. Then why on your website does it say that globe occlusion should happen sooner?
because the way that the sky works on the globe, the sky and globe geometry are merged one to one with the celestial and terrestrial sphere model. So on an observer standing, let me pull up this diagram real quick to kind of illustrate the point. That'll help. Give me 1 second. Central angle. Nope, it's this. Nope. One day I will get this correct. God damn it, I can never find it when we need it. Hang on 1 second. This diagram will be pivotal to help show the difference. Oh, that one? Yes, there we go. Theo in the central. God, I need to rename that. Okay, here we go. Okay, so let's see here. The question was, why is the globe earlier? Okay, so the sky and ground geometry are merged together one to one essentially. Now, an observer on a globe is already like their horizon's already deviated by the whatever the distance to the horizon is, and they can only perceive half of that. The same relationship holds true in the sky. So, in other words, the time or distance that the star has to drop or the time that it takes for the star to drop over that distance is shorter because it's already half of the arc length is already compensated for by the drop over distance. So if you were to go into Stellarium and make the time or make the angle of the star at the observer location 233, that would make it, we could look it up real quick while the globe predicts an earlier time. That would make the time 1840:38. And then if you add 2 minutes and 29 seconds to that, 2 minutes and 29 seconds is the full arc length. So if you start, dropping that star down over time, 1 minute and 15 seconds later from that starting position of 233, it's going to be at 217 for the observer. So that's going to be the same geometric alignment from the observer to the peak and from the observer to the star for the globe lads. Now like that's why it's earlier because it's already half the work's already done essentially, if that's easier to think about it.
So you can't explain why the mountain even though it's reverse engineered optics where they did the surveying, you're assuming the survey is correct because you're not doing actual theodolite surveying for this method. You're assuming their altitude angles are correct, yet you're claiming that the mountain on the globe is a different height. You're also claiming, even though it's lower, that it somehow occludes faster, um, even though that's all over the place with it's a complete contradiction. The method itself is yielding results for globe and flat. So, and you're claiming at the same time that the stellarium is pretty accurate with the astronomical refraction on. So pretty much it's just basically geodetic surveying repackaged from a flat Earth point of view because you guys want to psyop the stars for flatties.
Okay, so when I specifically talked about how the difference or I'm sorry, how the timing difference is different based on an observer on the globe and all of that, and your answer to that was that I couldn't explain it or whatever, like, and then referencing different mountain elevations. If that's your contention to it, do you think we're psyoping everybody? You know, okay, I don't know what to do with that, man. Uh, for the geometric intersection comparisons, it's flat Earth all day, every day. For the geometric comparisons for the globe, it's not showing that at all. For a corrected angle to match our timing difference, because the full arc length has to be traversed on a flat Earth, because there's no drop over distance, the observer isn't already aligned to a tilt to the horizon, then this is like what you're saying is that like you disagree with the method because you don't like kind of fully understand it.
No, I completely understand it, and you're not answering anything I'm saying. You can't even explain how the globe mountain would be lower if they surveyed it at the place that we all see it.
I mean, your question is like the drop over distance to the mountain. Like, what do you mean? The mountain elevation is the mountain elevation. Distances away from that are going to angularly change due to the drop over distance of, with respect to the coordinate system. So I don't understand I don't understand what you think your contention is.
Okay, so you're agreeing the mountain is at the same place in both models.
And it has two different elevations based on distance to it. Right? On a flat Earth, there's no drop over distance. On a globe, there's drop over distance between the observer and the mountain, right?
On a flat Earth, there's optical drop over distance. On a globe, there's drop over distance they claim is geometric. Either way, it's
Correct.
the same visual model, and you're comparing a visual line of light, and you're claiming you can discern between the geometries of two things that don't have different geometries. They just have different explanations for the geometry we see.
Well, they would have physically different geometries. That's why when we check with the light source, what would be purported as the light source, it's closer to the intersection that matches flat Earth for geometric intersections rather than what it would be geometrically for the globe. Because as you correctly stated, the globe has a specific geometric uh, prediction for it. And, that's not what's being measured in any of the cases. But what is, as we talked about earlier, how the refraction correction is spherically integrated. So any amount of actual real world variables get integrated over whatever the distance is, which compensates for the elevation. That's how 2 arc minutes of refraction gets turned into 13. So so the globe is literally taking what we optically see and the timing difference that makes flat Earth versus globe, and they're saying if we add a correction to it, we can have the same time you do, and that's being exposed through the exact geometric differences in all the measurements. So the methodology is clearly distinguishing between both models and their predictions, and then when we analyze the refraction aspect of it, like yeah, it looks like it's closer in some cases, but you got to understand too, they're spherically integrating whatever is there to the globe, which is presuming it, and then it's going to make it fit whatever it has to be, plus or minus real world variables, which will change it slightly.
Yeah, I just don't. I mean, I know for a fact no one understands how you have a different prediction for either model. You're not doing anything besides internally critiquing stellarium and the globe model.
Well, we're externally critiquing it by using the independent reference of the mountain. See, because the globe for the globe observer, the observer centric position is going to predict everything from, where the observer would see it, right? And they're going to claim that all of that geometry, is due to globe, and then any differences are refraction. When we go to the peak here, what we're doing, right? Like they might disagree with the methodology, but all we're doing is we're adding the arc length back to the position of the star, and we're seeing what elevation comes out at the time of occlusion. So instead of like, going to the peak or whatever, kind of thinking about it like that, you could just take this 206 here and add 27 arc minutes to it. And whatever angle comes out of that, if the Earth is flat, it should come out to be whatever the rise over run, elevation to the, whatever the rise over run angle to the peak is, which is, 233, 231 is what we predict. If the Earth is a globe and we didn't account for that drop, when we add the arc length back, it would make it higher than what we predict by the amount of drop over distance. So.
But yeah, even if like we grant that the geometries are different, even though it's just based on where we see the light and where we see the mountain, I still don't think anyone understands how you're um, measuring. You're doing this based on the fact that the occlusion timing is happening sooner on the globe when you have the mountain lower on the globe. Can you
Right.
explain that without just showing a graph of whatever
Yeah.
you're showing? It's not reality what you're showing.
Yeah, absolutely. The observer on the globe is already only perceives half of the arc length, right? So let's say I have to show the diagram to kind of help explain it, but let's take a look here. Actually, let me open it up in this so we can see it bigger. Okay, so I can move it around. Okay. Oops, it's the wrong one. Okay. So the globe lads, let's say we have an observer at B, he's on a globe, and there's a mountain here over at C. Now, the globe lads would never say that they could see the base of the mountain, right? Because there's curvature between them and the mountain. Do we agree?
Sure. If the
Yeah.
bottom is cut off.
Right. So their horizon, like how they're what they're able to perceive on a globe is always dictated by this midpoint of the curvature and whatever uh it would be. So if we're looking out at the horizon, whatever this midpoint would be, that would be, that's what's going to define it for them. And then things over this are going to be deviating down in elevation relative to the drop over distance of the arc length. Okay. So because they merge the sky and the ground together with the same model, right? They take the celestial sphere and the terrestrial sphere and they move it, they merge them together. They say, hey, we're going to merge them together at this center point, which is the same value as Earth's radius. So if you had an observer here and look straight up, the distance would be 6,371 kilometers, right? And the way that the sky, they say that the sky moves at 60 nautical miles per degree. Okay, well, to facilitate that, they use the comparison for this fictitious observer. So for an observer on the globe, when they're looking at the sky, they're only perceiving half of the sky, essentially. They only have to perceive half of it. So when that star for the observer is at an elevation angle of 2 degrees and 33 arc minutes, the star only has to drop 13 arc minutes of the total 27 arc length for it to be aligned at 217. And that occurs earlier than it does for flat Earth, because on a flat Earth, there's no drop over distance. So we're not misaligned to the horizon. So the star has to go the full distance over the arc length rather than being occluded early because half of the work is already done for him. And if it helps, I have a link here where I went into Stellarium at the different times that are shown on the spreadsheet for Pikes Peak, because it's the one that we're all the most familiar with. You can look at the timing differences for what the observer predicts for the intersection. So when this angle is 217, which aligns with what the peak, which aligns with the geometric peak for the observer at that time. That's why the timing difference is earlier, because it only has to go 13 arc minutes to align. It doesn't have to go 27. It doesn't have to go 27. Does that make sense?
You're literally using the star. Literally using stellarium to draw straight lines and measure the Earth, and you're saying that somehow the speed that the star is moving is different than they claim, even though you're using their literal software.
Well, their software is based on a calculation that's linearizing it relative to the fictitious observer. The difference in reality, there could be a difference in reality. No one's ever attempted to measure it using the true positions. Everyone that uses stellarium in the globe, how they use it, references the apparent position at an angle, and then whatever angle they're observing it at, they subtract the amount of refraction for that angle, and they reference where the true position would be to define distances and all of those things. So that's all we're using it for, because they have a predictive model of where these things should be. And so an observer on a globe should see the occlusion occur, a minute and 15 seconds earlier, because the star doesn't have to traverse the full arc length, which would take 2 minutes and 29 seconds. And you could verify that by, just looking at the angle and then the time and then playing it out and seeing when they line up. And another thing about, using stellarium real quick, that's why we add the arc length back to check. That's why we check from the peak. We're using that as the independent reference to check from for us. And so we should have a different elevation angle for the star at that time.
Hey, by the way, Gio, if you're here, YouTube feed is like freaking out. Stuttering. So just to let you know.
But yeah, to kind of end on that, I guess, would be what we see optically isn't the same as where things reside in 3D space. And so by using the occlusion timings, we have a reference to to an elevation angle of when an object was occluded, and it comes out
And so,
showing the
and
Earth
that's
every time.
that's based on you claiming that the mountain can't be refracted because the refracted position can't occlude a light.
Well, no one's ever shown a mirage blocking a light source, and it's pretty common knowledge that a virtual image doesn't have actual light rays emitting from it, so it can't cause interference from another light ray. So,
Okay, but the light source could be in an apparent position, and you could be drawing a line that's your line could be incorrect.
I don't necessarily disagree, but what we do agree on is when the star isn't visible anymore, it was occluded. So we can make references to where they say the light source was at that time. And if the light source was closer to our angle to the peak, then the Earth was flat. If we're above the peak by the drop over distance, then it would be a globe.
But if the star can be refracted, then it can occlude at a refracted time, just like a fish can be swim behind something that's actually not swum behind yet because you're seeing a refracted position of it.
I don't necessarily disagree, but what if the refraction amount value was spherically integrated to the difference in elevation between us, and any observation that was made, I took out my original prediction of drop and added it back in, and then we just had the same baseline.
Then you're just assuming stellarium to be accurate again.
No. They were that's not what that would imply. This is a separate situation, right? Because they have a specific correction, right? They're saying that there is refraction. We're saying, okay, well, how much refraction is there? Well, when you take the temperature and pressure values for Pikes Peak, for example, it comes out to be 1 arc minute and 44 arc seconds, which is, let's just call it 2 arc minutes for simplicity. So there's 2 arc minutes of real world value, but then for their model, they integrate that over the arc length. So it changes that 2 to a 13, which there's 13 arc minutes of drop over the distance. So by computation and spherical integration, they say, hey, if we add quote unquote refraction, then we can match your same angle. which is our flat Earth angle. That's a geometric argument, not a stellarium argument, because the refraction computation stuff, doesn't it's made up for the entire like system or whatever. So it's not just for the stars. So like if I was trying to introduce a magic correction in every measurement difference and it just so happened to be the exact amount that I said that I should have made the measurement by, you would be like, you would be very suspicious, I'm sure, right? You would have questions. And that's why we kind of disregard the refraction aspect of it. And when we go through and show the different discrepancies for refraction, like it never holds to the degree in which they say there is.
He's just ignoring everybody.
Hold on, guys. Hold on.
No,
You
I'm
guys gotta
trying to.
stop.
I'm talking
No,
to
not you,
QOB.
Alan.
Is someone here talking? Who?
Yeah,
Who
you
is
got
it?
Daza, Left Lane, and Wesley trying to chime in.
Oh,
No,
yeah.
The peanut galleries.
Yeah, no. So
We
guys,
don't need your questions, bud.
Yeah, guys. QOP and I are having a discussion, so please hold your questions until the end.
It's a one-on-one, right?
I mean, fundamentally, and from a flat Earth position, this is not its true position. The light that it's coming that you're seeing, and you're drawing a straight line through the mountain. So I don't know how you're claiming anything regarding the shape of the Earth with this, honestly.
So even if it's not the true position, right? The calculated position within their model of where they're saying it is coming up flat. When we draw a straight line to where the star no longer is because it got occluded, it makes a congruent triangle for flat Earth. If you're not interested in using it or whatever, like that's totally fine. But it's a geometric argument. It's based off of the occlusions, which provide us the obviously, like you said, that's not where the star truly is, but it gives us the reference point of where the closest approximation of where it last was to be a light source that's above an elevation that's either the flat Earth angle or the globe Earth angle. So
you're basically all you're highlighting is that stellarium might be a little bit off, and that the stars are occluding a little bit later than stellarium usually suggests. But you're also admitting, you guys admit, and I have you guys clipped up and admitting many times that it's close. You guys have gotten results closer to the globe method, the globe celestial theodolite method.
you can go through all of these measurements. Not a single one of them is closer to the globe intersection difference. The one that we talked about a couple weeks ago with SE Varley right here, where this value is 24, the globe predicts 22 drop over distance. Like the intersection difference, though, is the key part here because there's a specific arc length associated with the prediction. So when we look at this here, we have the central angle that's going to be 8 arc minutes. The drop over distance is 4 arc minutes. The star ended up traversing 13 arc minutes in total. So it lingered even longer than what flat Earth would predict by 4 arc minutes, which gives us this difference to come out to be 24. That's this is a residual of the arc length being exceeded. This isn't a measurement of curvature within the confines of the actual arc length that predicted the drop over distance for it. So this is a mathematical artifact of the arc length being exceeded rather than the occlusion happening at the time that the angle, or at the time that it would have aligned for the globe geometrically. So there's actually no, like, whatever you think you have clipped up, you can go through all of these anytime you want. They're all available. Not a single one of them is geometrically closer to what the globe predicts. And the reason, like I just went over for that one that Jesse was trying to make a big stink over, is because the arc length was actually exceeded, and it just so happened to be exceeded by the amount that the drop over distance was. So it gave us the error of 24, and then it doubled the error for the globe because now the globe is now off by twice as much as what they would have predicted for the drop over distance. That's why when we look at this, let me go back real quick. So when we go back and look at this, we're off by 24, but they end up being off by 45 over the same arc length. Well, how'd that happen? What happened because the star lingered beyond 4 arc minutes over the original arc length. And we're doing the analysis over the arc length, so any residuals get divided up between us in that regard. So there's actually no measurement that confirms the globe in this at all.
I mean, you keep saying geometric, but like the occlusion happening later should be the geometric prediction of the globe, just based on what you guys claim the geometries are, which I don't agree with because the globe is reverse engineered from what we see. So we're seeing the same mountain. I
Respectfully,
still don't. I still
sorry.
like. I mean, it's pretty good. Like gymnastics and math and magic you did from claiming to claim that the globe would predict it to happen sooner. But I don't think anyone here could steel man what the fuck you said when you tried to explain that. Especially, I mean, the main thing is that the geometries you're claiming are different, and you're claiming the mountain is lower on the globe. Yet your guys are assuming that the globe would have the occlusion sooner, and that the flat Earth would have the occlusion later. So, if you could try to explain that like with like in a scientific way and not like a math and magic way, which you guys, I got that term from you guys because I mean, you guys kind of taught me how to basically debate you, honestly, because everything you said for, last couple of years or whatever is about, apparent positions and how they used math and magic to basically ad hoc the globe. You guys are basically just cherry picking and doing some math and magic to claim you're proving flat Earth, even though you're just really just getting people from flat Earth to believe more parts of the star map of the globe.
Sounds like you have a strong bias against what we're doing, and you're kind of just saying different things after I speak. So you conflated the apparent globe angle to the geometric globe angle, which isn't which isn't what's measured here. And we talked about how their correction after the fact is just matching what we predict geometrically. So for them to even have a time to add refraction to, for there to be a lingering, there would first have to be an earlier occlusion time, which occurs because for the observer, they're already half tilted. The star in the sky only has to traverse half of the arc length to line up with whatever the geometric
Yeah,
angle
why are you saying that though? I don't. You're
the,
just claiming that, but why?
that's the geometry of a globe. That's the point of showing this diagram. Oops, that's the point of showing this diagram that we had over here, talking about the
The
hang on,
the
hang on, hang
sky
on, hang
above
on,
the
hang on, what?
mountain is
Hang on.
visible for on flat Earth and a globe. There's no uh,
They they don't
speed increase for being on a globe. It makes no sense.
queue up. Listen though, they only perceive half of the drop because for them the sky and the globe drop are 1 to 1. So the star only has to drop 13 arc minutes for the observer to intersect with the angle at 217. That's why. It's pretty straightforward.
No,
Okay. Just no. All
you're
right.
saying that the distance,
Yeah.
the geometric distance a star needs to drop is less on a globe.
The geometric distance that the star would has to traverse on the ground, essentially, like if you were thinking about it in terms of like, you know how they say this
Not
every,
traversing
yeah,
anything on the
yeah.
ground. It's
Well,
we are seeing a
just
lens. We are seeing a
just
hemisphere lens. They are
yes,
claiming the hemisphere lens is a globe model. So
correct. So
where
so
we
just listen.
see is the same. I
Let
don't.
me walk you.
Dude, this
Let me
makes
walk
no
you.
sense what you're saying, dude.
I'm trying to walk you through this. Just give me a second. So as the star is angularly dropping, right, the globe lads would also say that the GP of the star is moving, right, across the surface of the Earth, 1 to 1, right? Because that's what creates the drop for the
Yeah.
observer. Okay. So the observer only needs to observe 13 arc minutes of drop before it intersects. Now you could say that you don't like I'm just making it up or what have you, but you can just go into Stellarium and look at the true position when it intersects for that. It's literally the earlier timing. It's this time right here. It's oops, that's the wrong mountain. 1 second. It is 184204. It's in the geometry of that, right? Like if you wanted to understand geometrically why, it's because they only perceive half of it. They only need to perceive half of it. That's it. So saying like
Half of what?
half of the drop of the star. before it intersects with the mountain peak. They're already tilted. The ground did half the work for them, essentially.
Dude, this is all like they're just what is that? That has the ground just because their globe is spinning doesn't make anything different about you're literally
Q-Up,
using stellarium to do this.
Q-Up, nobody said anything about spinning, man. Like,
You just said
it's
the ground did half the work. I thought you meant like the globe like spun in the way or whatever.
elevation different wise. The difference between a sphere, an observer on a sphere and an observer on a plane is they're always, they only perceive half of the horizon. They only perceive, and the same applies to the sky. That's how they worked in the celestial horizon being at the equator, like relative to relative to an observer anywhere on Earth for the half of the hemisphere. That's how they relate it. So that's why it ends up being an earlier time. It's a geometric aspect of them being on a globe. Now, they say, well, there's refraction, and it just so happens that it's the exact amount of the drop over distance. So, which creates the timing difference for it to match what flat Earth predicts for the full arc length. So if the star isn't dropping at 60 nautical miles per degree, like their model predicts, and it's lingering, then the flat Earth measurement, rise over run to the peak, is going to be substantiated in every measurement. And that's what happens. And then they come in with refraction and they're like, oh, but look, if I take out what I predicted as drop, then I can match your baseline. That's an apparent correction based off of assumed geometry that isn't present, and we only assumed one geometric, you know, calculation, and we got the correct result. We got the result that's closer every time.
So can the atmosphere, different mediums of the sky, maybe of the ether, all these things, can they cause the occlusion to happen at different times?
I wouldn't disagree with that. And I've even shown at the beginning of a lot of the early Self Theo episodes, we would show Goose's measurement with the light source and adding the refractive medium and then showing the angle change at the occlusion time. It absolutely would. But the question is, how much refraction is there really? Because all they're doing is taking the actual amount of refraction that's measured and then spherically integrating it. So they can't actually know if there's that much refraction or not.
All right, so you're just basically just debunked your whole thing, claiming that the occlusion timing can happen in any time depending on different atmospheric effects.
Yeah, but how much? Does it affect it to the exact amount as what would be predicted as drop every time? That would be preposterous, man.
I have no further questions. I didn't think you were going to concede to that. That's not good.
It's our premise, dude. We open up shows with it.
Your
Like,
premise is that the way that you're timing this thing, drawing the line, can be affected by the atmosphere and other mediums, and it can be drastically it can be different than a straight line that you're hoping is 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 actually happening
well, the
because you want
straight
to
line
use it
comes
to
from after
measure.
the occlusion. The straight line comes from after the occlusion of where it once was. So, like, it's not the same thing as what you were just trying to say there. So,
Yeah, well, you said the occlusion timing can happen different based on different effects.
okay, and you agree as well. So do you agree then if we use spherical integration of the model that we're asserting that however much refraction is there is what's measured? Because if that's your assertion, you might as well be a globe lad.
No, I don't assert to know any of the mediums or claim that there's a geometric difference between the globe model and the flat sorry, I don't claim that there's an optical difference. So the geometries are different, but they don't even really account for optics, and therefore what we see is the same thing, but they just claim it's something different. So
That's our premise that the globe is an optical phenomenon. That what we see is optical. That's why we do the geometric comparison to the angle to the peak, for the rise over run to the peak and for what the globe would predict. So, because there's a difference in the actual geometry, but the optics, there wouldn't be. So I think I mean, honestly, dude, is there any other things you want to end on or whatever? Or was that pretty much it? You good?
Yeah, I mean, I don't know what else, what more is there? You can't explain really like why the occlusion is happening quicker on the globe. You're saying it's because the globe geometry. I'm not sure how that affects what's above the mountain peak in the sky, which is all completely open to the air and is visible and
Yeah.
is happening at the same rate that we see stars occlude every day. It's pretty consistent. So it's not different on the flat Earth. It's the same consistent star pattern. You're claiming the occlusion can happen different because of atmospheric effects.
Dude, you're like reconflating different aspects of my position to make your argument, man. There's a specific rise over run angle to the peak, which is based on the time that it would take for the star to traverse the full arc length. On a globe, it doesn't have to do that. You can look at the intersection for what the observer-centric predictions are. Like, I, you might not be able to grasp what I'm saying at this immediate moment, but to say that I haven't explained it is, at this point, is you know
You've explained your reasoning, but your reasoning isn't really proving any any actual explanation for why the occlusion would happen sooner. It just doesn't. You didn't really say anything, honestly. You're just referring to the geometries and the math you're doing itself as the proof for why the occlusion would somehow happen sooner, which is still not even. It's like what is how much sooner? What's the discrepancy between like flat and globe, like as far as the time? Like it's
Fantastic question. So for flat Earth, we predict that for the star following sidereal time in 60 nautical miles per degree would intersect with the peak for flat Earth using rise over run at 1843.18. The star was occluded at an angle when it was at 233, so it was a little higher. So they got occluded a little bit before the full central angle, 2 arc minutes to be specific, which creates an 11-second discrepancy between prediction for flat Earth and what was measured. For the globe, they predict 1842.04, which is when the star's true position for the observer over that arc length would be intersected at 217. And that created a discrepancy of 1 minute and 3 seconds. Now, if you add our differences together, that is the expected drop over distance there. But the drop over distance of the arc length, so if you take this 13 arc minutes, it takes 1 minute and 15 seconds for the star to drop 13 arc minutes. If you go into stellarium at the observer location and put the star at 233, that'll rewind the clock by 2 minutes and 29 seconds. And 1 minute and 15 seconds later, as you press play, that star will have dropped 13 arc minutes for the observer, and it'll be aligned at 217, which will create a time of 1842.04. And then over here, we have their refracted correction, which is the exact amount of drop over distance. So in other words, if there was no drop over distance, their time would be our time. And that's exactly what is shown here. So they have a geometric prediction that none of them want to adhere to. They would like to introduce a corrected position, which is just our position for what it would be geometrically. And they're trying to establish the optical conditions for the occlusion. But in doing that, they make the Earth flat. So
I mean, it sounds like really good globe propaganda. Honestly, you're claiming the globe mountain is lower, and you're claiming the occlusions are happening later than than stellarium suggests.
I mean,
It's kind of fun.
all the globe lads want to use the refracted position because it changes the timing difference. See, if you see the drop over distance here is 1 minute and 15 seconds for it to drop 13 arc minutes. Well, that amount of refraction, right, 13 arc minutes is also 1 minute and 13 seconds. So, because it's a rounding error on the arc seconds, that's why the timing is slightly
Yeah,
different.
they're just defending stellarium's accuracy. They don't
Yeah,
really
they,
grant
right.
your prediction or what your
That
claim the globe should be. So
and no, and that's totally fine. But for them not understand, like ignoring the geometric argument of it, is where their worldview has collapsed, because to recover what the globe predicts optically, they have to remove what they predicted as drop over distance every time to match us. So we're geometrically flat, they're optically globing. So like even though they don't admit like the only globe lad to, admit this or realize the significance of it was Mike, which is why he changed his position from being a globe lad to a flat earth lad. None of the globe lads want to acknowledge this because it leads to a conclusion. There's a clear geometric difference here. And when they use the apparent position, they recover our angle every time, which is geometrically significant. And understanding that aspect of it is a pivotal piece of of this. So
Yeah, I don't believe Mike's a flat earther.
that's totally fine. But can you believe that the rise over run to the peak yielded an occlusion that was 11 seconds off of prediction real time, and that the globe added a correction that matches our prediction that made it 10 seconds off by removing the drop over distance that they originally predicted? So irrespective of Mike's position, like do you grasp the significance of that?
I just don't grant any of the things the rise over run. I think can be in apparent position. The mountain. I think the star is obviously in an apparent position. It's like the most extreme apparent position is the stars. That's why they appear to drop drastically from the sky. Like
Well, they
the
linger.
this is
It's not drop. They linger outside of what their model predicts. But go ahead.
well, I mean, their model predicts that you can draw straight lines to the stars, and you guys are doing the same thing. So
No, we're drawing a straight line to where an occlusion occurred based off of where their model predicts it should be. So we're not claiming that this is like the exact position or anything like that. They have a specific model that they're asserting describes the geometry of not only the ground, but the sky. And we're testing that through timing differences of occlusions. And what we found in every scenario, every occlusion matches what flat Earth predicts using rise over run to a geometric angle, not an apparent one. And when the globe lads come in, they add back the drop over distance as a refraction correction and say, look, it's the same for what we optically perceive. So
can anyone besides Alan Steelman why the globe predicts? I mean, why the globe prediction is an earlier occlusion?
Not that I've heard of.
Or is it because it's like he's acting like I don't understand? It's like nobody understands what you're saying, dude, and you probably don't understand. That's why you can't explain it simply.
okay, if you subtract 13 arc minutes of refraction, what position would the star be at?
For like, what kind of like riddle is that?
It's a straightforward question. If the star's refracted position is 219, right? There's 13 arc minutes of refraction. If you remove that 13 arc minutes of refraction, what position is the star for the observer?
From 219.
It'd be 206.
Okay, I don't know what that's like proving.
Well, for the observer, for that true position of the star to get to 206, it had to first get lower than 217, right?
Okay.
And the time that occurred was at 1842.04. That is the geometric position that we're comparing. And that's when it would have occluded. And when we get this,
why is it sooner on the globe?
because the star only has to drop half of the arc length. It doesn't have to drop the full arc length.
Does anyone know what he means?
Yeah.
Yes.
Yeah,
Can you explain?
there's no geometric intersection based on the angular height, right? So we're saying it only appears to get lower in the sky. It's not geometrically getting lower. So it doesn't occlude half the arc length because the Earth isn't curving up to meet it. On a flat Earth, that has to traverse the entire arc length, which is what we're seeing. On a globe Earth, it would have to do half because the Earth is rising up to meet it. That's the difference. That's what half gamma represents.
Well, Shane agrees with you.
Well, even if he didn't, right, you could deduce this yourself by if you took 13 arc minutes of refraction and you didn't have that as the correction for the globe lads, right? So if you added, or I'm sorry, if you subtracted 1 minute and 13 seconds from the time of occlusion, you would be back at the geometric intersection angle that they would have predicted for the earlier intersection. So like you can verify this yourself and understand it. Whether or not they agree to it or who can steelman it is irrelevant. These are things you can do yourself to like it's straightforward. If adding this time difference makes it match the longer distance that it takes to drop, then it
Then there
therefore
is
would
no drop.
it would therefore follow that there would be an earlier intersection for this to be added to begin with. So it's like whether or not you understand the mechanism of why, it doesn't matter. It still occurs. Still.
So I've got a question then. So if we were to do a occlusion observation of Catalina from Oceanside, which is approximately 65 miles, Catalina has a 2,000 foot tall mountain range, and according to the trig on that, taking the tangent of it, it should still be something like 20 arc minutes or something like that. A silhouette that's 20 arc minutes, 2/3 of the height of the sun tall, of the silhouette of the island should be seen against the sun. Occluding the sun with its silhouette if the Earth was flat. But we know that even in June, when the sun is at the correct angle to be directly behind the island, you never actually see the island silhouette. You can't see the island at all from that location when you're standing on the beach 6 feet.
Do you have a question
So,
about like the presentation?
but then my question is, shouldn't we, if what you're saying is that the refraction doesn't affect the occlusion, shouldn't we still see, when we're seeing the silhouette, when we're seeing the sun, shouldn't we see the island silhouette in the sun? We shouldn't see the full disk of the sun if the sun is directly behind the island, right?
Yeah, it should be similar to Mount Canigou, right? If that's what you're asking, it should be. You should
It
see
should be like
you
that. Yeah,
should
it
see
should
the
be like
silhouette
Mount
of it.
Canigou, because it's impossible for the refraction to somehow show you the sun but not show you the silhouette of the island, which is occluding the sun, right? Which we know it should be occluding the sun, 2/3 of the sun based on the trig, right? So from Oceanside, you should be able to see the silhouette of Catalina against the sun, but we don't. We don't ever see that island.
I'll have to take a look. I never heard of that.
Okay, I'm done.
Okay. Beast, did you say you wanted to say something about the occlusion timings?
Yeah, just the simple fact that, half of the arc length, what that means, queue up. So basically the observer to the mountain peak, that's the full arc length. So basically for the globe, there should be a middle point to where it's cut off because of curvature between you and
The curvature of the globe has nothing to do with anything above the mountain where the occlusion is happening above the mountain.
curvature of the globe has nothing to do with it.
It
Okay.
does, because the position of the star as viewed by the observer is already going to be deviated. That's why the intersection occurs at 1842 relative to that arc length versus 1843 for flat Earth. So it only has to drop half. It doesn't have to. It never has to drop the full amount. So
What full amount of the entire 360 degrees of a globe?
No, the 27 arc minutes of the arc length. So whatever the distance is between the observer and the peak, that's called an arc length. That angular amount, whatever it is, the globe or the star on the globe would only have to drop by whatever half of that angular amount is to intersect with whatever the peak would be every time.
Bro, it's honestly like you're saying you say the mountain is lower on the globe, yet you're saying somehow I really don't know what you're saying, but
because the star is already lower. The star is already lower for the observer by half of the arc length. So it only has to travel half of the arc length to intersect with the peak for their angle. Like, even if you don't understand it, you could go into Stellarium and just like look at it and see the differences. It's like when it's aligned here versus when it's not aligned. Like this is,
With refraction on or off?
with refraction off. And if you add refraction, okay, listen, Wesley, with refraction off, and then when you add refraction to it, what happens? It adds another 1 minute and 13 seconds back. So it adds the other half of the arc length back, and then the full occlusion time gets almost recovered, which is the flat Earth angle.
Yeah, but we see the star with refraction on. We see that where it is with refraction on. So why
And
wouldn't you
we've
start with that?
we've already went over how that's done through the refraction is computed through spherical integration of the arc length, which is why in every scenario where there's an elevation difference between flat Earth and globe Earth, the refraction happens to be the amount of the arc length or greater than the arc length. I'm sorry, happens to be greater than happens to be the exact amount or greater than the drop over distance of the arc length, which is the half gamma, the half of the arc length. So,
What's the or for? Is the or the inaccuracy?
no, when did I say or? What was it about?
It's just you're claiming you can measure the difference between flat and globe, which I don't know. It's like there's no real explanation for why they're different. Because we're not on a globe, which means they looked at the flat Earth and they made the globe model. So the idea
Yeah.
that they're
So,
actually different doesn't make any
so
sense. Stellarium is based on when things like where you see the stars and when they occlude and everything. So you guys
no,
are just
it's
finding out
actually
that
not.
Stellarium might not be very accurate.
It's
As
a,
accurate as they want it to.
it's actually not quite that. And most of your position is our position. What we perceive isn't the geometry of what is actually happening. And that's what the occlusions show. That's why optically it looks like this. That's why optically, when you reference their bottle, which is based on optics, we get this intersection difference that occurs earlier because they're making the observer centric prediction and comparing it to where it would be on a globe, which is changing their baseline to the horizon, which puts that star at a lower angle by whatever the drop over distance is to it. That's why
I
it only
honestly
has to.
think
That's why it all. Hang on, dude. That's why it only has to go half. That's it.
go half of what, dude? Does anyone know what he's saying when he says that?
Half of the distance, half of the arc length, half of the
No,
drop in
it
the
makes
sky.
no sense. It makes no
Does
sense.
anyone besides the three people that are pushing this understand what that means?
Nope, the star is traveling down for both models at the same rate, and for some reason they use curvature for
And they're
interpolation.
claiming the globe mountain geometrically is lower, so it would
Right,
take longer
correct.
to get to the globe mountain peak.
And they use curvature, but it's
No,
obviously not being
no, no,
blocked by
no. Hold on
curvature
one
because we
second,
see it being
Wesley.
blocked by the mountain before curvature.
1 second, dog. We're not saying that it would be blocked by curvature. That's retarded. We're saying that the elevation of the observer is already tilted by whatever the drop over distance
Oh,
to the
Shane
arc.
said that.
Hang on,
Shane
would
said that
be
in chat.
just stop for a second. Is already tilted by whatever the drop over distance to the horizon is for the observer. So the star only has to drop half of the arc length to intersect with the geometric peak at the end of the horizon there. That's why. And you keep changing things that you're saying about what we're about our position, and it's really annoying because it's like you don't even know what our position is, and you're just kind of saying random things to disagree with it. And I'm
Who, me?
yes,
Me or
you.
me?
You specifically.
What did I strawman?
Oh, whatever you just said before Wesley chimed in and I had to correct him first
Oh, I
was what
strawman, but he doesn't know what it is. Okay, cool.
yeah, I had two things in mind and I had to talk to two people who were talking over each
He
other
doesn't remember the
to agree
strawman.
with
Okay,
each
cool.
other. Okay. Well, we can pull it up on Earth Awakenings and listen to what it was real quick. You want to do that?
If anyone wants to look at my YouTube in like a week or so, I debunked celestial theodolite on my YouTube, so it's coming.
Yeah. 1 second, lad. Is in your and you
And there is any. I
that's why it
honestly
only
think
has that's why it all hang on, dude. That's why it only has to go half. That's it.
Go half of what, dude? Does anyone know what he's saying when he says that?
Half of the arc length, half
No,
of the
it
drop in the sky.
makes no sense. It makes no
Does
sense.
anyone besides the three people that are pushing this understand what that means?
Nope, the star is traveling down for both models at the same rate, and for some reason they use curvature, but
And they're
it
claiming the
doesn't.
globe mountain
Yeah,
geometrically is lower, so it would
right,
take longer
right,
to get to the globe mountain peak.
and they
They're claiming the globe is geometrically lower, so it takes longer for the globe to intersect with the mountain peak. The globe predicts
Yeah,
that the
no,
mountain
that's
is
what I'm
geometrically
claiming.
low.
I'm claiming
One
it would take
second.
longer.
Hang on 1 second, dog. You just said that we were claiming that. And then you were like, oh, you can't repeat the straw man. So I just went back and watched it. So listen, the thing to correct you on as you're talking over me now, we're not going to do that, QOP. So just settle down for a second. So the globe predicts the earlier occlusion time because the star only has to drop half of the arc length. We predict a later time because we don't predict that the star is following the 60 nautical miles per degree at the lower angles, and it has to traverse the full arc length. That's what causes, or that's why it's a later time than us. Them adding refraction is them adding back the earlier time that they predicted, and then saying, "Look, it just happens to match the flat Earth angle when we use our spherically integrated refraction correction that exactly compensates for the drop that would be predicted." So two separate things there that needed to be corrected. And this isn't the first time you've said that throughout this conversation. You've said, you'll just randomly say a different thing than what was just said. And like, I think we've reached the pinnacle of what we can talk about in this conversation. So I'm going to mute you now, get your final thoughts off. We'll take final questions and then we're going to wrap for the night, lads. Go ahead. Jed, hold on 1 second.
Claiming
Sorry,
what?
sorry, start over. I didn't hear you.
So first of all, I was just saying that you guys claim that the geometry of the globe mountain is lower. I said that based on that, the occlusion should happen later. I'm not saying that you guys claim the occlusion should happen later on the globe. Um, so yeah, so that's not a straw man. That's just me steel manning you and then claiming what I think should happen with the occlusion timing. But what you just said, which is finally you added actually a real explanation for why the occlusion should happen later for flat Earth, is that the the speed of the stars would slow down at near occlusion angle for
Yeah,
flat Earth.
they're not following the 16 nautical mile per degree relationship. That's just the
Yeah, why?
calculated position of where they assume it is. I have no idea
Yeah,
why,
why?
because it's just a nonlinear rate. I have no idea why it doesn't follow it, other
So
than the fact that the Earth
why
isn't
does
a
the flat
globe.
Earth get that? Just, you don't know why it happens, but the flat Earth gets the
Yeah,
later occlusion.
yeah. So part of their assumption is they're saying that like we know that the star is following this geometry. We know where its true position is. We know where it's at in 3D space, et cetera, et cetera. That's what defines, distances and using the stars for celestial navigation for them, is them saying that they know. We're saying we don't know where the true position is, and we don't predict that it would follow that, especially at the horizon. That's where there would be the biggest deviations. And when we take the measurements, that's what's shown. So we get they get an assumption of linearizing the rate. We're contending that and then showing that the measurements are supporting what we're saying versus what they say. And their spherical integration refraction corrections recover the flat Earth angle every time. So, and you also said earlier, real quick before I wrap up, you said, how you think it should happen. Well, how you think it should happen isn't how it happens. You can go and verify it yourself in Stellarium and look at the timing differences, and then just logically think about, if there's if the occlusion is predicted to be 1 minute and 15 seconds earlier, and they're adding 1 minute and 13 seconds to correct, you know, what what is that 1 minute and 13 seconds relative to? Oh, the earlier intersection.
Is it always later, or is it sometimes accurate?
Is what always later and or
The
sometimes
occlusion.
accurate. Oh, always later. That's why every measurement gives the rise over run to the peak. It like recovers the flat Earth angle every time.
Well, you guys say the opposite sometimes.
We've never see like you're just saying like we just said the opposite. We've never said that.
I
Hang
can't
on 1 second.
I
One
can't
second, dog.
generate.
Hang on. hang on, just real quick. You're saying that we're saying a different thing. We went over this earlier. I went over all the measurements and we showed that the geometric intersection is always in favor of flat Earth. It isn't until they add the literal drop over distance back as a refraction correction to match the same timing difference that we predict. Go ahead.
You know, you guys have said that it matches closer to the globe, like three or four times or something.
All right, dude. In what context? Is the context the apparent position? It's never the geometric intersection, the thing that we actually argue.
I have one of the data sets on my video. I'd have to go check it, but I don't have my computer on.
All right, well, just let me know next week or something. All right, we are going to wrap up for the night, lads and ladettes. We're going on 3 hours. What a girther. All right, we will pick it up next week. Like I said, we went over the plane stuff today. We went over the ray tracing, the spherical integration of actual measurements to fit the model, which end up recovering the flat Earth angle astronomically every single time as a feature of the integration to the assumed sphere, which is why every time we analyze the refraction at the occlusions, it matches or is greater than the central angle itself, fully compensating for that angle. If we had the freedom to add a correction to our timing, wouldn't you know it, we'd match it every single time. But the purpose of that isn't to add corrections or see how many corrections we can add to increase the accuracy of our measurement. It's to see what the raw geometric implications are when we check what the elevation of the star would be with respect to the elevation of the peak at the time of occlusion. We're either going to be off by the drop over distance that we didn't account for, or the globe is. And it turns out, like Mike showed earlier, when you add the expected drop over distance back to the intersection difference that was measured here, this difference, it equals what the globe mismatched their prediction by, showing that the air, cancels out exactly. So there is no drop over distance. The globe model is unsubstantiated. The optical argument of how we perceive is, what the globe is built upon, and the geometry to support that geometric claim, because the measurements and other things don't go along with it. They literally add back the drop over distance and recover our angle, and then want to argue about an apparent globe and not the actual globe geometry. The geometric aspects of this experiment show that the Earth is flat. Otherwise, the measurements would be reversed, as we showed with the Pikes Peak, where if the occlusion occurred in the way that the globe predicts with the earlier time, when we add the arc length back, we would be above an oops, that's the wrong one. We would be above an elevation by whatever the drop over distance is there. So we'll be back next week, lads. We got some new data to go over, so we'll get to adding those. I like how Daz is trying to talk over me mid outro. It's crazy. We'll be back next week to go over the new data that we collected. What was it, Sunday or Saturday? One of those 2 days. All right. Thank you, guys. And now that that's wrapped up,